Let me know. I think the audio is good. Cool. Alright. Today I've been asked to do a little bit of like easy, beginner stuff, teaching functional programming rather than just doing, advanced, AGDA and dependent types all the time. So I'm gonna go through something that I've been doing at work a lot, which is the functional programming course from Data61. This is formerly known as like the NICTA course. Sometimes it's still usually called the NICTA course. NICTA is no longer really a thing anymore though, so Data61 functional programming course. This is now maintained by some people up in Brisbane, the Queensland Functional Programming Lab. They're now maintaining this this project, and it's just a little I don't know, it's just a repository full of Haskell exercises. It's very good, really good at teaching functional programming. So I'm gonna go through this, have a go at this, just show like I don't know, just show how I derive the answers and how I usually teach it. So hopefully people get a little bit out of it if they haven't done a little bit of Haskell, and even if you've done a little bit of Haskell, hopefully people will I don't know, get some learn a little bit about how I teach it anyway. I've got 2 classes going on at work where I teach this class. Let me bring up some things. Actually, so OBS was having some problems this morning, so let me come over here anyway. Cool. Okay. Now the first thing that the FP course says, so in the README there's a couple of things. First thing in the FP course is to go through the syntax. So here's the steps. We'll go through each one of these. So first thing is to open up a new file. And open up GHCi. So the syntax is Haskell has in Haskell, we can write our first program by looking like this. Whoops, ignore that. I'm gonna say x equals hello. Y is 2. Z is true. So what we've done is assigned these things. Each one of these is an assignment, and this is a value on the right hand side. So whenever you see an equal sign, you've got a value on the right hand side. And on the left hand side, in this case, we've got our identifiers. So this is showing assignment. We're going to go through this pretty quickly. Yeah. So this is these things on the right hand side of values. So this is a string value. That's some sort of numeric value, and this is a boolean. And we are assigning these to identifiers. We're assigning these values to identifiers. So one thing we can do is add in something called type signatures, and whenever you see these double colons, that means type. So what we're saying here is x has the type. Whenever you see this double colon, you should be reading it as has the type. So x has the type string. And we can write here y has the type int, z has the type bool. I'll also write and this is this value here is a list value. And what we're saying is W has the type list of integers. We'll go through a little bit of syntax around the around list and things later on. What it means to say like list of integers. But you can just read it. Just the main point here is that this is a value down here. That's what you need to know. That's a value. And W has the type. So this double colon means has the type. That's what you really need to know at the moment. Yes, so let's talk about functions. So we can write a function that so we can write this. This is a function. So this is saying I am a function that takes in an argument a, and the value of computing this function is a plus 1. And so we can write down a type of this one, which is int to int. So this is a function from int, and the result is int. And we can also write we can also write it like this. This is equivalent. These two lines here are equivalent. There's no difference between these two. And if we want a function that has two things, we can say like that. And what's interesting is that this, so what we've done here is written a function that takes two things. I'll talk about that in a minute, but we could also write that the same as this. Whoops. So G is a function that takes an A and a B and gives back a value from using that A and B. And what's interesting is that the type here looks like this. It's a function that takes in an int and gives back a function which takes in an int and gives back an int. So really when I said that G takes two things in, that's not quite true. G is a function that takes one argument in, then returns another function which takes another argument in. So in Haskell, all functions in Haskell, let me know if you're confused by this, but all functions in Haskell take one argument. Always, only, ever, one argument. Says in the README, we approximate without spoken language. Yeah, like we're a bit, when we're talking about this, sometimes we say like, you know, sometimes we say that, sorry, my webcam's a bit weird. Sometimes we're a bit sloppy when we say that, you know, G takes two arguments even though really it only takes one. So so the way that this associates is like that. So that's what it really means, but we can get rid of the parentheses here, and it looks like that. And they're all equivalent. Cool. Okay. Let me know if there's any questions about functions. I'm trying to go through this really quickly because I think a lot of people that probably watch my streams know Haskell a little bit already. So I'm trying to go through this pretty quickly. But let me know if there's any questions around what functions mean. Let me know if you've got questions around what it means for functions to only take one argument. Like in Haskell, it is true that all functions only ever take one argument. That's a really important thing to understand. So we can also write. We've been writing these identifiers, and at the moment we've just been using like single character letters. But you can also make identifiers using symbols basically. So I could write what's a good one? I could write this. Actually, let's go through this first. So So I can write this, right? This is me using a function called plus. I'm adding 1 and 2 together. Oh, I just realized that my chat has not been working this whole time. I'm sorry if people have been... my chat was not showing anything for some reason. Twitch chat's a bit weird for me, I'm sorry. People have probably been asking heaps of questions about this. Well, hopefully. Let me know if I missed anything important. I'm really sorry about that. Chat's working now. I can see that. Thank you. Let me know. Was there anything important that I missed? I'm really sorry about that. I saw I had viewers and was wondering why I didn't have anyone chatting. Sorry about that. Why Haskell and not C++? Haskell for everything I do, Haskell is far more practical. What's the topic of the stream? Sorry, I'm gonna I had some people ask me, can you do something, can you do like beginner Haskell? So I'm going to go through the FP course, and I'm going to spoil some of the answers to begin with, but I'm basically going to go through FP course. At the moment I'm just showing off, I'm just going to go through how I teach FP course basically. Yeah, how I teach FP course at work, and I've got 2 classes that do this FP course. So the topic of the stream is for me to show how I teach FP course, even if I'm going to do it a bit quick, because I mean, it's a bit boring when you like when I've got a class of 10 people or something. It's, you know, I can go through and I can take my time in that, but I don't really want to spend too much time on syntax and stuff. I imagine half the people in the stream already know the syntax of it, so I'm gonna go through the syntax pretty quickly, but I'm gonna teach how I teach this FP course. Yeah, Atlassian does teach functional programming. I teach functional programming at Atlassian. Yeah, we've got at some point we had about we had probably like 10 people or so doing this FP course. There's like another group of about 10 people that also have been doing this FP course, not with me, but with the people that actually maintain this, which is the Queensland Functional Programming Lab people. So these people travel around Australia and they teach functional programming. So if you're in Australia, get onto these people. They'll come to basically, if you have a company that's interested in learning functional programming, talk to these people. They'll come to you, usually for free, and help you learn functional programming. That's basically their job. The Queensland government is funding functional programming. So if you are in Australia and you want someone to teach you functional programming, get onto these people. But yeah, so Atlassian took advantage of that offer, and in Sydney, these people came down to Sydney and taught them functional programming. And so I've been working with a team that's actually in San Francisco. So I do it remotely. But I've been teaching this class to basically two different groups in San Francisco. So that's the topic. I'm going to go through this FP course and show basically how I teach it, go through some of the beginner ones. First of all, I'm going to show syntax. I know this might be boring to half people, but this is basically how I teach it. Usually a little bit slower because I don't know. Syntax to me is a little bit boring, so it's just something that you have to take time to go through, and I don't really want to spend that time on stream. I think it's not really the right environment for it. Cool. So any questions so far any questions about the syntax or anything? It's awesome that Atlassian is invested in functional programming. At work we do I work on this thing, Marketplace, and we do I don't know, we just do lots and lots of functional programming on this service. So a lot of it is in Scala, which is not a great tool for doing functional programming, but it is possible, and so we do it, but it's not ideal. So what I am trying to do at work is get people to learn functional programming, but in a way that's easy, because learning functional programming using Scala is not easy, really not easy. It's like when you go to teach functional programming using Scala, there's a lot of apologizing. So it's like, here's how we write a function in Scala. Oh, but look, now Stack Overflows, and exactly, it's good for learning trampolines. So there's something called a trampoline which fixes the Stack Overflow problem. So there's basically all these problems that when you start doing functional programming in Scala, you basically have to find all these different workarounds for it. So that's why we teach Haskell. And this is a really good course that I've been teaching. So I'm going to go through this. I'm going to keep going with it. Yeah, let's look through some more of the syntax, and hopefully we can get through the syntax pretty quickly and we can get onto some of the actual exercises, because those are pretty cool. Alright, so operators. So this is an operator that we've used, so we can write it like that, or we can write it like this. So basically, operators you can surround in parentheses, and then it becomes something called prefix notation. So this is prepended between two arguments. Or we can put, you can use something called infix, which is where you take off the parentheses and you can put it in between two things. So this is how we usually add two things in Haskell, but we can also write it like that. And that means that this plus no longer is an operator, it's just a function. Atlassian make use of Nix? Yeah, we absolutely use lots of Nix. That marketplace website that I showed just before, this is all deployed. We've got probably like 5 different services. They all use Nix, and they all use Docker. So we use Nix to build Docker images, then we ship them out, because Atlassian's got like an internal platform as a service, where you can basically ship services using Docker. So we use Nix to build everything and then put it into Docker images, ship it off. Possible to implement finger tree in Haskell? Absolutely, yeah, there's a finger tree library. Oh, showing off because he implemented? Awesome, good job. Cool. Prefix, yeah, cool. Okay, yeah, so another thing is that with these identifiers that we've been writing, here's the same as, this is plus, right? So this G function is plus. And so we can call this function by just giving the arguments like this. This is the syntax for calling a function. So this is giving 2 arguments to G, but we could write it like this as well. And this is called, this is like infix on normal identifiers. So usually we have this rule where plus can go like that, or it can go like that, and those are equivalent. And similarly, this normal identifiers like G can go in between two things like that. And you just surround it in backticks, and that's what we call like infix notation for normal identifiers. Cool. Okay, so let's write one more thing. So we have this function a to a, right? We can say, let's be a little bit. Let's go that. So remember, this is read as has type of. And what we've said here is I has type of a to a. And what's interesting is that these are lowercase. Lowercase a in Haskell means polymorphic. So generics, if you're thinking about it in Java. So all of these ones up until now, we've used capital. See how we've used capital here. We've used capital to begin with this one. When you start an identifier with a lowercase in a type, that means it's polymorphic. So we're saying for all a, give us back an a. So in something like Java, it would look like this. So given an a, and that's pretty ugly, but that's how you would write it in Java. So it's just a generic. You just got this little generic thing in there. Yeah, that's a rule that generics in or polymorphic types in Haskell always start with a lowercase letter. So let's go through data types real quick. Let's make a data type. Actually, let's start with a more simple one. So this is defining a data type, and the data type has actually let's I'll change the name a little bit. Okay. So this is a data type, and the what we're writing is this is the type name. So the thing on the left hand side is the type name, and the thing on the right hand side, this is called a constructor, data constructor. So this is a type, and this is a data constructor. And so we use this constructor just like, it's similar to like how you would think about a constructor in something like Java, where you can use the constructor to construct something of a type. So this is a way to construct a person. So this is what we would use to construct a person. And the constructor takes two fields. takes a string and an int, so we can think about that as like name and age or something like that. So the way I would do this is person. Remember that we can say this has type of. So Brian has type of person, and Brian. Remember, we use the constructor. This is how we constructed the type. Use this this constructor to construct a type. So I can write it like this, and we have. Now we have Brian, which is a value, and the value represents a person. And what we can also do is I'm going through this really quickly. I'm sorry if anyone's really new to Haskell, because you're not quite going to get all the syntax from this. But this is a way to write something we call a sum type, which is that Z is a type, and it has two constructors. So when we separate by a pipe, we're actually saying here's another constructor. So we can say J has type Z and J is X. So we get to choose one of the constructors whenever we construct Z. So there's two different constructors, and we get to choose which one. And using this, we can implement something like our own booleans, for example. Oh, something else I should have mentioned before was that identifiers can have ticks in them. Can have this apostrophe character. And there's a convention around that. Sometimes we put them at the end just to say, like, if an identifier is already used, we just put a tick at the end. So if you ever see that in our code, it just means that we're trying to basically escape variable bindings. All right. What else can we do? Yep. One thing we can do is we can use this thing called deriving. So we can give it a list of things to derive. And so here we're saying derive show, and this will give us like a toString. So I'm going to load this up in the REPL. Whoops. Ignore this part. Usually this would work, it's just that I'm doing it in the fp course directory, which means it won't work. But here we go, we've got this now. So deriving show means now I can type in the REPL and it will actually print it back out at me. So this is like a toString, so I can give it a value and it will do a toString. So I could say X actually takes a string. So this is similar how before we say a constructor takes two things. We can also say in these cases where there's multiple constructors that they take things. So you can see here that it's printed it back out, and that's what that show does. And we can also say derive eq. So if I reload this back up, I can say J is the same as Y. False. So eq gives us this equal sign. So that's deriving. So we can write a function over this thing that we just made. So because we've got multiple constructors here, I can write something like this. And when you see a constructor on the left-hand side of an equal sign. So see how we've got a constructor here on the left-hand side. So whenever you see an equal sign, you see a constructor on the left-hand side. That means we are doing something called pattern matching. So here we're saying that if the argument to k is an x, then here's the implementation for that. If it's y, then here's the implementation. So that's when you see a constructor on the left-hand side of an equal sign, that's called pattern matching. There's also another form of pattern matching, which looks something like this. So if you see it on the left-hand side of an equal sign, that's pattern matching there. But you can also do case. Whoops. You can also use something called case, and that looks like that. So anywhere where you don't really have like a declaration, so these are called declarations, these things that we've been doing so far. Anything on the left hand side, well, anything that's got this equals is a declaration here. And all of these things have been declarations that we've been running so far. But inside of declarations you've got expressions. So anywhere you can write an expression, you can use this case statement. Well, this case expression. Yeah, and what's interesting is that whenever you see constructors on the right hand side of an equal sign, we are constructing data. So I think we had, yeah, so here we are constructing data up here. And we are constructing data here. So this is on the right hand side, constructing, on the left hand side, pattern matching, which is a form of deconstructing. And we'll really quickly go through something called type classes. So before we were doing this deriving thing, we can get rid of, let's get rid of that. We can write our own, so instead of using deriving, we can write our own instance of this thing. Actually, that's fine. Yeah, so we can say, here's how to compare these things. And so we have to implement our own equal now. And remember on the left hand side, it is, it's pattern matching, so let's pattern match on the case that we have two x's into equals. In the case that these two are equal, then we just compare the strings. In the case that we get anything else, so underscore is something that you need to know as well. Underscore represents, we don't care. Underscore just means that we don't actually give it an identifier because we don't actually care what it's going to be. So when we've got two x's, they're equal. But when we probably should do that. When they're both y, they need to be the same as well, don't they? They need to be true. Cool. So underscore just means in the other cases. So this will match when you've got one x and one y on the other sides. That's what that represents. So what we've done here is we've defined something called a type class instance. So we said for the implementation of eq for z is here. So we've just written an implementation of eq for z, and that's called type class instance. And so eq is something that's already defined inside of the standard library in Haskell. But we could write our own class, and we could say, I don't know, let's say toString. There's already something like that, but. And so when we write a class, remember that is the eq requirement for eq only equals? Yeah. All the other ones are derived from that. All the other ones get derived from this equals being defined in Haskell. It is possible for you to implement other things, but you don't have to, because the implementation for not equals is not equals, if that makes some sense. So that's the default implementation that comes out when you write eq. So you only have to do double equals because this one's derived. You can read it. You don't have to put, it's fine. Okay, so we've got this, we're making a toString type class, right? Remember lowercase, when you see lowercase type, so this, when we're running a class, we take a name of the class, and then we give it a type, and the type is lowercase because it's a polymorphic type. And so in here, when we use a function, we can say that polymorphic type to a value. And so toString, we can write like a instance of toString for int, for example. So I can say, this is how I convert ints into strings. I mean, at the moment we'll just use show. Let's do instance toString for bool. So I can say toString of true is the true, and toString of false is false. So this is what we call a type class up here, and these are instances for that type class. And so what's interesting about type classes is that there's an infinite number of instances, potentially infinite number of instances for a type class. If I write a type class, and then you write a data type, you can write a instance for your data type for that class. So it's basically a way of like having what we usually call open polymorphism, or like open extension to things. So whenever I write a class, you can implement that class for your own data type, if it makes sense. I mean, not always. Like there's some type classes where it doesn't make sense, but you don't want to implement every single type class because that's not possible. But you want to implement, you know, a lot of them to make your data type useful. Is there any other resources you recommend over Learn Your Haskell book? Yes, I wouldn't recommend Learn Your Haskell so much anymore. It's just a little bit outdated and a little bit, there's some not great things about it. I would recommend this book, Haskell Programming from First Principles. It's not the cheapest book. It's about $60 US, which depending on your exchange rate might be quite a bit of money. But it's really good. It's a really good book. There's something in there for people that are like still like intermediate to advanced people. You can go through the composing types and mono transformers, and actually motivates. It's the best motivation I've seen for mono transformers by far. But yeah, it goes through all the basic stuff as well. You heard that type classes are most similar to interfaces in that. Yeah, it's not. I try and avoid saying that they're similar to interfaces because there's quite a few differences. There are some similarities, but the similarities aren't huge. I wouldn't say that they're very similar to interfaces. You can kind of think about that, but that thinking will break down at a certain point. It's worth it. Sold my old Xbox for it. No regrets. Cool. Yeah. Hopefully this book is better than an Xbox. I really recommend it. I did read the Mono Transformers chapters and I was blown away by how good it was. It's really, really well written. Really good. Highly recommended. Cool. Okay, so we got through the syntax. I'm sorry if that was boring to anyone. We'll go through some of the exercises now because I think that's where the interesting stuff is. So the first exercise is the optional module. Actually, let me show how you would do this. If you were going through... oh yeah, there's the tools as well. Okay, yeah. So I'll go through this. Yeah. So when you were writing, when you were going through this course, we use just GHCi. That's all you need, just GHCi, and then you can, if you just open up that, then you've got access to everything. It actually automatically loads up this course. So it loads up every single file in the thing. So you can just type in, whenever you modify something, just type in reload, and if it says okay, that means you've implemented it, and it type checks. But every time you type in reload, it will do the type checking and everything. And you can use this thing called type, and that will give you out. Whoops. Let's try that. Yeah, let's load up my syntax thing again. Okay, so I can say what's the type of X. So we can spell that out. Type. What's the type of X? And we get back this. So that shows us type. We can say info, and info is useful for data type. So we can say what is Z, and it will actually print out what the two constructors are for Z, and it will show us what instances it has. So it has eq and it has show, so that's really useful. We can say info X, and it'll just print out the type. It's just similar to type when you just use it on a function. Or we can say info, and we wrote toString. So we can ask it about a type class, and it'll show us what the definition of that type class is, and also what instances are available. With class, you define an instance with you define an interface. With instance, you define an interface adapter for a particular type. You can get a long way with that thinking. It's a little bit not quite right. We can go into details about that later on. Yeah, we can talk about. I think if we it's a while off. You can think about that for a while. Yeah, that'll do for now. Okay, right, you can just evaluate values inside of the REPL as well. That's fine. We've already gone through that, gone through that. Okay, we've gone through most of this. Yep, I'm going to ignore doc test for now. Okay. Cool. So we've been through that. Okay, so some of the things that we should know is reload. We'll reload all the modules in our course. Thanks for the follow. So when we're going through the course and we implement some of these, modules, you type in reload and it'll reload it up. can look at the type, look at info to find out. Yeah, so those are the main tools. You're looking up types. Sorry, looking up map optional. Looking up types, looking up using info to find out things about types, and then reload. Those are the main things that you'll be doing if you do this course. Okay, so we're going to go through and look at exactly one first. So that's under SRC, so source, course, slash, optional we're going to look at first, yep, optional. So this brings up our optional module, and so there's a couple, I think all the exercises are done in here? No, they haven't been. Okay, cool. I think that's the first one, optional. Oh, okay, actually, there are two things. So exactly one, let's look at exactly one. So this is all the code in exactly one. Exactly one, for people that already are familiar with Haskell, this is called the identity functor. What we're defining here is a data type exactly one, and what's interesting, I didn't show this before, but data types can also take parameters. So this is actually like, you know, type parameter is a polymorphic type. Remember, lowercase types are polymorphic. So we're saying exactly one takes some sort of other type, and it's the way to construct it is exactly one. So also I didn't go through is that data types and data constructors can have the same name. They live in different namespaces, so they can have the same name. But what we're saying is the data type exactly one has one constructor, exactly one, and that exactly one has a field which is a. So if you have you can have an exactly one of int. So let's play around with that. So we can have exactly one test. And we can say what's the type of that. So this is the constructor, and that is a field that we're giving to the constructor, right? Ignore that thing. Ah, that's a bit annoying. Let's get this. Here we go. Exactly one true. So exactly one true. So this is the constructor. That's a field to the constructor. So that's like an argument to the constructor. And it has type. Remember, double colon has type. Exactly one bool. So this bool, because we're given true, and that's the type. So there's a function run exactly one. Remember, pattern matching on the left hand side. If you see constructor on the left hand side of an equal sign, that's pattern matching. So we're pattern matching and getting out the A. Pattern matching on exactly one, getting out the A, and we return it. So it's a function from type exactly one A gives back the A. And we got these functions, so mapping over it. So given a function A to B and exactly one, we get back an exactly one B. You don't really have to worry too much about this. All you have to do is just recognize the syntax. So that's a function type up here. That's we're binding to that function up here, and then exactly one A, exactly one, and we're getting out the A, and we pattern match because it's on the left hand side of an equals. When we see data constructor here, on the left hand side of an equals, pattern matching. So that's something to recognize. Pattern matching here. So you need to pattern match your pattern matching. Recognize that that's pattern matching there. And that we're just extracting out these things from the arguments to this function, and that's very similar. And here we have Flatmap is bind. They're equivalent. Flatmap and bind. If you've seen this bind name might confuse you. If you've been doing Scala or anything, you might call it Flatmap. This is Flatmap. And here we are defining instances. So remember, instance means that we're going to create an instance for a type class. This is a type class here that we're defining. So what we've done here is we've imported things. You can actually import things and give it a name. So we've imported this library, this module as a name, and we've imported control.monad as m. So whenever we see m dot or p dot, we're just specifying which module to get it from. So this one comes from applicative module. This applicative identifier comes from the applicative module, and we're saying write an instance for this applicative type class for the exactly one data type. And that's the implementation there. Right, yeah, in Scala, Flatmap is not quite bind. Yeah, a lot of the time it's not quite bind. We often treat it as bind, but it's not quite. Also, if you get confused at any point about any identifiers, you can go and use lambda bot. I've got a lambda bot called profunctorbot, so hopefully that will work. Maybe not. Hopefully my bot's not dead. My bot's probably dead. Oh, there we go. Okay, so if you use question mark type and then you type in an identifier, or you type in an expression, you'll get the type of it. So if you're confused at any point, use that bot. Okay, so that's exactly one. We'll look at validation real quick. So validation is actually this is actually really useful data type. They've got some Java on there for some reason. Don't really know what that's about. So validation is a data type, takes in a type parameter, and it's either an error or it's a value. So you can read this as or sometimes. There's two constructors. Error, which takes an error. So here, one thing I didn't go through either was type aliases. So this is a type alias saying that error is just a string. So to create an error, you give it a string. So whenever you see this error here, this ERR, that's the same as string. So like they're equivalent. Type aliases and the underlying data type are exactly the same identifiers. Like they identify the exact same thing. So it's just a string. So error takes a string, and value takes an A, which is the parameter we passed into to validation. So we have a validation of int, and the two ways to construct it would be to give it an error with a string value, or to give it an actual int and say it's a value. So let's play around with that in the REPL real quick. So what are the two things? So value, I could say value true, and the type of that is validation bool, or I could say what's the type of error? So we can say this is any validation. So I could say that is a validation bool because this is a type parameter and it could be anything. So I could actually say that is the same as validation bool. So we can also use it in expressions. So when we've got an expression, we can say this has the type this now. So I can actually say if we've got a value on the left hand side and it's a bit more generic than what we want it to be, we can give it this, which says make it this thing. So it will just basically instantiate this A to be a bool in this case. So we can say take out the generic parts and make it into this part, make it into this specific type. I don't know what that Java is. Maybe it's meant to represent what this data type. Yeah, that's what it is. It's meant to represent what this data type is in Java. So it's got two constructors is what they're trying to say. It's got that constructor, it's got that constructor. Okay, so this is a function. Remember pattern matching, left hand side of the equal sign. Constructors that are on the left hand side is pattern matching. So that's pattern matching, that's pattern matching. This is a function. We'll go through the dot. We'll go through the dot later. We'll explain dot later. You can ignore the dot for now. Data constructor on the left hand side, pattern matching, pattern matching. So you can see that like when we have a data type that's made of these values, when you've got like what we call sum types, because they got two different constructors. When you've got more than one constructor, you call it a sum type, and because these are sum types, pattern matching is very common usually to work on sum types. So this is the whole module. All you have to do is basically recognize the syntax. You don't have to think too much about it. Just recognize the syntax. This is just a way of working with data in Haskell. And this is what we're going to be aiming at writing. So the first module where there's actually exercises is to use this optional module. This is the one that's got exercises in it. And so optional is something. Optional is a data type that takes another type. And it has two constructors. Full, which takes the value of that type, A, or it's empty. So there's two ways of constructing an optional, right? So there's full, where we can give it a value, or we can say empty. Those are the two ways of constructing an optional. So the first exercise is map optional. So I'm going to throw it to the chat. When we have sum types, what's the way to work over sum types? If we're looking at validation, remember validation, what was the way that we were working with this sum type? If we get a sum type as an argument, like this one, sum type as the argument, what do we do with that value? How do we work over sum types in Haskell? Case, yeah, that's getting there. I'm looking for like a specific phrase I've been saying over and over and over again. Let's give these names. So we've got F and we've got the optional. What can we do with this O? So we could use case, pattern matching, exactly. So we use pattern matching. So the phrase there was pattern matching. So we use pattern matching. And what's the two cases of optional? Does anybody remember? Has anyone forgotten already? What's the two cases for an optional? How will we find out? There's info. So if you go info and then you give it the type name, it'll tell you what the constructors are. So there are two cases, there's full and empty. So when we do pattern matching, we have to do, so we did close to some or none, very close. We're defining our own optional types, so it's not like the built-in Haskell one. The built-in Haskell one is slightly different identifier names and has a different name. But it looks like that, full or empty, yeah. So to pattern match, we have to match on both of those things. So we've got full of a map optional. What was it? Empty. So I'll go through this thing as well. So if you prefix an identifier with an underscore and then you try and load it up in your GHCi, you'll actually get something called hole, and it'll say there was a hole here. And this is, remember, has type of. So to do this under this identifier has type of optional B. And also this is another thing to look at. So basically look at these two lines. Look at the first line here, and then look at this thing, relevant bindings. So this tells you what you got in scope, and that tells you what you need to implement. So we need to implement optional B from these things that we have in scope. So those are the interesting parts. Some just nothing, none, full, empty, optional, option, maybe. Can they just agree? Yeah. Okay, so if we look at, well, the convention in the FP course is that just above the thing that you have to implement, they'll put tests. So here's two tests, that if you map optional on an empty, you get back an empty. And if you map optional on a full with some function, it'll run that function on the argument. So hopefully people can see how, you know, kind of how this is, how given a full 8 and a +1 function, you're meant to get full 9. Hopefully people can kind of see the relation between, you know, this argument, and then that result. Okay, so we can do the simple one, right? So map optional of empty looks like it's always empty. You know, we're given this function, but we don't actually do anything with it. And remember, when we don't do something with a function, we can replace it with underscore. So when we match an empty, when we pattern match on an empty, we get back an empty. So that's the implementation for this empty part. If we go through the full part, what is the constructor? What will we do to optional? How will we construct an optional, right? Because we've got this, let me reload this back up. First argument says that this hole, this underscore, has to be replaced with a value that returns an optional B. How do we create an optional B? Does anyone know what's the ways that we could create an optional B? Bonus points if you choose the wrong one. If you choose the wrong one, that'll be good. What's the two ways to construct an optional? Which way should we use to construct an optional? Awesome, you chose the wrong one. Awesome, thank you. So we could say this is empty, right? So there's two ways to construct an optional. Go back to info. So we had let's do that for now. So there was two ways to construct one. So we had empty, which is one case. We could just say empty there. So that's the bonus points for saying the wrong one. But there's two constructors, empty or full, right? So we could just put empty there, and this will compile. But it's not that it won't pass this test. We have this test up here. So we could get this to compile by putting in empty, because empty is an optional B. Empty is an optional of anything. You can have optional of absolutely anything, and empty is one of those, because empty doesn't take any other values that line up with the types or anything. So empty is an optional B. So I could put that in there, but then it would fail this, because we say map optional, full 8, and so we match down here, full 8, that would match, and then we say full 8 is empty. So that would not pass this test. So that's the bonus points for being the wrong one, because it doesn't pass the test. So the alternative is that it has to be, like when we have a full, what do we always get back? We get back a full, so it has to be full. And so I'll put in another hole here. Reload that, and I need to, yeah, there we go. So we have a hole here. So to do one has type B. So read this, to do one is a hole. And its hole is that it has type B. So we have to replace this to do one, underscore to do one, we have to replace it with a value that has type B. The other thing to check is the relevant bindings. That's the other part. So basically the two things to focus on when you write these holes is look at the first line here, which will give you the type of the hole, and then look at the relevant bindings, and this will give you the things that are in scope. So all of these things are in scope, but if you look at these two, look at the first two, we've got a function that goes A to B, and we have an A. What can we do with those two things? What can we do with a function that's A to B and an A? I think we've already seen the answer. Apply the full FA, exactly, yeah. So F is a function that takes an A and gives us back a B. Remember that we need a B, because what we have to do is make a value that has type B here. So F returns a B, so if we just pass this A in here, then we'll get back a B. And that type checks. So that's the first answer to the FP course exercise. We'll go through bind next. Let's go through all of optional. There's not a huge amount in optional. There's only a few different functions to implement. So I think we've already implemented like a quarter of it. So let's implement bind optional now. So notice that these are very similar. So bind optional takes a function that returns a new optional, and it takes an optional. And so in the empty case, we get back empty, right? And in the full case, we do something with the full. We'll go through what we do with it later on, but let's take a look at this. So we have two arguments. We've got a function and we have an optional. What can we do again? What's the way that we deal with optionals? What do we do with when we want to make a function that works over optionals? There's a particular thing that we did last time that we did with an optional. Someone knows. Someone mentioned the keyword that I'm looking for, the key phrase I'm looking for, and what we would do with an optional to implement this function. Something that we just did with map. What did we do with map? No one's playing my game. No No one's mentioning the phrase I need. This particular phrase that I would look for. Pattern matching, awesome, finally. Okay, thank you. Pattern matching. We would pattern match. So we've got two cases, right? We've got function and we've got our optional pattern match on the left hand side. Someone please answer poor Brian, exactly. And what's the two cases? What's the two cases for optional? There's two cases. Optional has two cases. What were they? Either I've got massive latency or people don't want to play my game. This is more exciting when I do it in person. Not... I refuse to be the teacher's pet. Alright. Full or empty? Awesome. Cool. So, empty. And what did we say in the tests? What does the test say about empty? Result is empty. And remember that if we're not using the function, or if we're not using an argument, replace it with underscore. If we're not using an identifier, just replace it with underscore so that we don't even have it in scope. Or empty or full. So let's load this up. Found hole. We need to give back an optional B. What we have in the scope is a function. That's A to optional B, and we have an A. So this is similar to what we had before. There's two ways to construct. We deconstructed and then we constructed the optional. With this one, it looks like we don't even have a constructor to choose from, because what we're doing, if you look at this, if you basically just do get directed by the types. You got a function A to optional B. We need an optional B. So how do we get that? Well, there's a couple of ways to make an optional B, right? We could say empty. Empty is a valid way to create an optional B, but then these tests won't pass because you need to do, we need to have full coming out. So we could write full, but then we need a B. We don't have a B. So if you basically just keep looking at this and trying to find a way to get to the implementation based on the types, look at the relevant bindings, look at the whole. This is a really useful way to work with types in Haskell. Is you write in this underscore identifier name. It'll say found this whole, give you the type that it needs, and then you just look through the bindings to try and figure out a way to construct a value of that type. And the way here is we've got an optional B for F, so that means now instead of, so if we were to say we're going to use F, now the goal, instead of being to find an optional B, because we've found a way to make an optional B, now the goal has become how do we find an A? We actually have one in scope, so that's A. So the implementation would be to use F and use A together to create an optional B. And so the implementation is FA. Hopefully that made a little bit of sense. We should be able to run these examples they've given us. Whoops, I'm all over the place. Here we go. So we should be able to run all these examples. So let's run this one. So what this means is, given a full of 8, if you follow through the implementation, you'll actually see what this is doing. It takes out the 8. Puts it in as n, so n here is 8, and then runs this function, and that's the implementation. So if 8 is even, then the result is n take 1, which is 7. So yeah, full 7. That's what we get back. And if we run that function again, but with 9, I think it is, we get back 10. So even, n is not even because n is 9. So otherwise we go n plus 1, so then we get back full 10. So that's how that works. Hopefully that makes some sense. This is actually, so far we've been implementing this optional module, and this is actually how we would implement the module in Haskell. The actual data type is called maybe in Haskell, but this is exactly how it's implemented. There's nothing fancy about it. It is really just taking a data type. In the other case, it's called maybe, and the constructor is called just, and nothing. But this is exactly what you do to implement Haskell, which is you create a data type, give it some constructors, maybe you derive some stuff, you give some type class instances maybe, but then you just write functions on the data type, and this is what Haskell is. It's just writing data types and then using them. So if you've got the kind of the things that we're doing is constructing types. So constructing types by using constructors, and then deconstructing types by using pattern matching. So it's really Haskell is really just constructing things and deconstructing things, and that's all of what Haskell is. So what we're doing here is actually exactly what the maybe module does, or the maybe data type in Haskell does, which is it's a data type with two constructors, and then there's a heap of functions on those things that pattern match it down and reconstruct it back up in some sort of way. Maybe not even reconstruct it back up, basically deconstruct it in some way. And that's all that Haskell really is. So what we're doing here is exactly what the built-in Haskell libraries do. Nothing fancy. Does take a bit of exercise a bit of practice to get used to, but that is all that Haskell is. Okay, so remember that identifier operators, we call these operators when they're non-alphanumeric. So these are operators. But operators, when you put them in parentheses, are just like functions. So what we can do here is, when we write A (B), that is the same as writing, those are the same. And when we go to define it, we can write here, we can pattern match. So, because we've got an optional argument, we can pattern match. So let's say empty. So we'll do that. So this is one way to implement it. There's actually a couple of different ways we can write this syntactically. We could write it like that as well. And that's the same. So we can either use prefix notation or infix. Infix being this one, and prefix being when it's actually before the arguments. So we'll go infix. Why not? Okay, so this is left-hand side of this operator is the first argument. Right-hand side is the second argument, right? So in empty, what do we do in the empty case? Return back the second argument, right? So we've got empty on the left-hand side of this operator. The implementation is the right-hand side. Oh, whoops, I've done the wrong one. Empty. Hey, how's it going, Malachi? We're going through something called the FP course, which is done by, it used to be called it's often called the NICTA course, formerly named the NICTA course. It is now maintained by the people that run the Queensland Functional Programming Lab, and they go around Australia teaching this course. And so I teach this at work. I'm just going through, just doing some of the exercises just to show how I usually teach it. I know people wanted to learn a little bit more of. Yeah, you've heard about it. Awesome. Yeah, it's a very, very popular Haskell course. It's really, really good. Really well done. So I teach it at work. I teach a couple classes at work on it. Some other people at work have recently been doing it thanks to the Queensland Functional Programming Lab. And so I'm just going through how I usually teach it. Just going through it quickly. People wanted to see a little bit more of like beginner Haskell. I got asked that a couple of times. So thought I'd do this, just go through some of the exercises, just show some basic Haskell, just show how I explain the exercises, even if I'm kind of rushing through them. Some of the terminology I use, some of the ways that I explain it. So just going through, showing some basic Haskell and how I teach it. Cool. Okay. Okay. So we'll keep going through this question mark. So in the case that we have full, notice that it just gives back the argument to full. And it actually it doesn't do anything with the thing on the right hand side here. So if you think about it, when you've got something that you want to ignore, you can just do an underscore. So we're going to ignore the right hand side, right? So underscore means don't even give it a name, so we're not even going to have that in scope. If we come over here and type in reload, and because we've gotten rid of the right hand side, we've put an underscore there saying that we're not going to even use this, because I can see here we're not going to use it, right? Put an underscore, and then what we have is that we need to get back a to-do-2, so that we have to replace to-do-2 with an with a value that produces an A. What do we have in scope? Oh, we have X, which is an A. So we don't have this underscore in scope. That's not even, doesn't even say it's in scope, because not even given it a name. So all we have is an X, which is an A. So it's actually by giving this thing an underscore, we've been directed towards a solution. There's only one solution now, which is to give back the X. So by not giving this, well, we could say that was a B, right? And then let's go through that. So if we did this, right? Now I've got two A's in scope. Which one do I use? Now I have to think about it. I have to think about it because I've given this thing a name. I've given this thing on the right hand side a name, so I have to think about what the possible implementations here. So there's actually two. I could say the implementation here is B, and that would be the wrong implementation. So me looking at the tests, I can actually decide not to give this identifier, and then GHCi will actually direct me towards the right solution because I haven't given something identifier. So that's a really good trick that you should keep in mind. If you know you're not going to use an identifier, don't give it a name. Use an underscore. And this I mean, I can keep going on about that, but like this ties into something that we call point free. Later on, we'll talk about point free a little bit more, but ties into point free a little bit. All right, so I think this is the last exercise in the optional module. Go through this real quick as well. So what's interesting about optional though is that we have two options that get passed in. And so the thing that we've been doing with optional so far is pattern matching. So now we've got two things that we can pattern match on. We've got two things. And which one do we want to pattern match on? Well, if we look at these examples, when we have a full on the left hand side and we've got an empty on the right hand side, we get back the left hand side. If we've got left hand side and right hand side, we get back the left hand side. If we've got an empty on the left hand side and a right and a full on the full on the right hand side, we get back the right hand side. If we've got both empty, then we get back empty. So what can we do here? We want to pattern match. I can't actually remember what we want to do. We want to pattern match on the right hand side first, I think, and if it's empty, then give back the left hand side. Sorry, now let's pattern match. If we pattern match on the left hand side, what will happen, right? If we, in the case that we've got the left hand side is full, notice that if the left hand side is full, it doesn't matter what the right hand side is, does it? We can just say underscore. But we do actually have to, I think that's right, yeah. If it's, oh, thank you, Weechley, thank you so much for that, thanks for that cheer, thank you. Thank you, Weechley. So, yeah, so left-hand side, if we have a full on the left-hand side, then we use the left-hand side. If we, I think in the other cases we can use just the right-hand side, right? So in this one, we just say use the right-hand side, and then in this one, just use the right-hand side. So full, we want to match on the left-hand side first, and then otherwise we can just use the right-hand side. So let's do that. So we have full on the left-hand side. Doesn't matter what the right-hand side is, right? So this is the implementation. So here, this might look a little bit confusing. Stick with it. This plus operator on the left-hand side. If we get past a full, actually, I'll write it slightly different. I'll write it similar to how we've been writing things before. That might clear it up a little bit. Something like that. Let's look at this first. It might clear it up a little bit more syntactically. So this function plus, if the first argument is full, then we don't care about the second argument, and so we can just get back full. But in the other case, so we can actually, when we do pattern matching, we can actually say instead of matching on both cases, instead of going full or empty, we could just say full or anything. Actually, let's go empty though. That's a little bit clearer. Yeah, let's go that. Yeah, that's better. Actually, that's better. Ignore what I had before. So we've got full on the left-hand side, or as the first argument, give back that full. If it's empty, then just give back whatever's on the right hand side. And so this will match if it's both empty. If they're both empty, then O will be empty, so that will give back this one. So they'll pass this test. Let's run the tests. So the way that matched is first one was empty, so it gives back the second argument. So that doesn't. So as long as the first one is empty, we'll get back the second argument. And in the case that it's full on the first argument, we're going to get back. Going to get back the first argument. So that's how to make sense of that one. So we pattern match on the first argument, and we either ignore the second argument or we use it. Cool. So that's the optional module. So now you know everything there is to know about option. That's it. That's option. Cool. And now the next one is actually going to step it up quite a bit. We're going to go through list. I want to go through list because list is cool. Lists get pretty intense because it's a recursive data type. What we've done here, right? So we're defining a data type list, which takes a type parameter t, and it's got two constructors, nil, or we pronounce this cons. We pronounce this one cons. So remember that operators can go infix or they can go in prefix. So this is the same. Those are the same, right? So we can write it either way. I'll just comment that out. Those are the same, so that's how to read it. If you're struggling to read it like this. Read it like that. So hopefully that makes some sense to people. We've got two constructors. List has got two constructors, it's got cons and it's got nil. That's something to remember. And to create a list, you can use nil. That'll construct a list of anything, so it can be empty. We use nil to represent empty. And cons we use to represent head and tail. So a list can either be empty or it can have a value, a head, like it can have a value, which we call the head, and a tail, which is the rest, like the rest of the list. So it's a recursive thing. So we could say like we could have a list that looks like. Let's go through this. So here's a list. So that's a list. We can say 1 cons nil, and so this is a list that just has like it's a singleton list of 1. Or we could say 1 cons 2 cons nil, or 1 cons 2 cons 3 cons nil. Yes. So in Haskell, usually what we use is just a single thing. So usually we use this. This is normal Haskell here. This is like the standard library Haskell. This is the list that we've just written. So this is this list up here. Yeah, we've defined our own, exactly. Yeah, so this is our list module. So we've just put a dot on after it just to signify that it's our own list. The normal built-in one looks like this, but this is our own one. So these are all lists here. So these are all lists of integers. Each one of these here is a list of integers. And this is what it would look like in normal Haskell. There's different syntax, like you can write in Haskell just that, and it desugars into that thing. These things are equivalent. Okay, and so here we've got an infinite one. Don't focus on this too much, but you can. This one is making an infinite list. So this is a list that just counts forever. And so what it does is it just keeps using the constructor, because it's a recursive data type. It can just use that constructor, the list cons constructor, forever. And that's all it does. Is it just starts off at 0, and then cons it uses 0 to cons onto a recursion. So a list that then starts from 1, and then that cons 1 onto a list that conses from 2, which it keeps counting up. So it's basically just an infinite list of made up of conses. So we call these cons. It'll just keep constructing up new heads with new tails forever. Okay, and so we're going to get a lot of practice using these. So I won't go over them too much, but the way to think about, actually I will go over them. I'll describe what they do. I won't really go into too much details about how they're implemented, but what you can think of, right? This is how to think about fold right and fold left. A lot of people think have really broken thoughts about fold right and fold left, and that's from a lot of the standard libraries that are around that supply fold right and fold left that don't do a good job of them. If you use fold right and fold left from like Scala or from JavaScript or something like that, they're not quite right. They're not actual, like they're not how fold right and fold left should really be. So I'll go over what fold right actually does. This will take some time. So fold right is constructor replacement. Really important. Actually, I'll put those in capitals. Really important. When you see fold right, think constructor replacement. Whenever you hear the word fold right, think constructor replacement. Don't think, oh, I'm folding from the right. Don't think that. Think I am doing constructor replacement. That's really, really important. We're not folding from the right. We're doing constructor replacement. And I'll explain what that means. We're doing something called constructor replacement. So when we have fold right, so fold right takes two things. It takes a function and a value, and then a list. So it takes three things, but these are the two things that are interesting, right? So if we do fold right, let's say plus 0, right? So what we're saying is this actually represents cons. This thing, remember list has two constructors, right? So the two things that fold right takes, these two arguments, which seem kind of arbitrary, are not arbitrary. These two things represent the constructors. So remember that cons takes an element, it takes a head, and then a tail, and then creates a list for us. Or we give back, or we have nil, which creates a list for us. So where we have B in this case is kind of like the way to construct a list. And the A here is like the element in our list. So what we're saying here is that everywhere you see cons, replace it with plus. So let's say with our example, if we're doing fold right, let's just do that. Okay. So fold right, let's say we want to fold right with plus and 0 with our list that's 1 and 2. We've got a 2-element list, 1 and 2. We want to fold right over that. What we are saying is, first argument is what we want to replace cons with. So we are saying everywhere you see cons, so remember our list looks like this. Everywhere you see this cons operator, replace it with plus. And this 0 represents what we want to replace nil with. So replace nil with 0. So this is what I mean by constructor replacement. We're replacing, when we do a fold right, we are replacing the constructors. List is two constructors, remember, cons, nil. We are replacing those constructors with a value. So our value for the first one is plus. So we are replacing cons with plus, and we're replacing nil with 0. So that's really, really important. When you're thinking fold right, think that we are replacing the constructors with some other value. Replacing cons with plus and replacing nil with 0, for example. Or we could have fold right, so to put it into, like to generalize a little bit more, so if you think about its constructor replacement, think 1 cons, 2 cons, 1 cons 2 cons nil is if we're going to just replace it with like some sort of generic F and an A, then remember that backticks. Remember the backticks, because that means that it doesn't matter what function we pass in there. We're just gonna put that function in between these two things. So everywhere we see cons, we just put the function in, and we can rewrite that to look a little bit like this. So this is what fold right is equal to, replacing the constructors. And so eventually you will come out something like that, and you can think like when people say that, you know, it's kind of like folding from the right, because it kind of turns out to look like that. There is something where that's kind of kind of looks like it's folding from the right, but really what we're doing, what we're really actually doing is constructor replacement. That's the real thing to understand. We're doing constructor replacement when we do a fold right. Really, really important to understand that part. I can go through some more examples, but we're gonna practice that a lot, so I'm gonna leave it there. We can talk more about fold right because it's really important to get fold right. Now, what's interesting is fold left is not as useful. Everything fold left can do, fold right can do. That's important to understand as well. Fold left is the way to think about fold left though is for loop. So these are very different. Like fold left and fold right, it's not about directions. They're very different functions. And the most important one is constructor replacement. Fold right is like the most important one. Coming from JS, I have some great misconceptions about fold right. Yeah, right. Yeah. Fold right, constructor replacement. Fold left is for loop. Those are the ways to think about those two functions. So if you have a for loop, let's say, let's write some JavaScript, right? So var x, just call it accumulator, right? So let's write for loop. So we can still, because we're using plus and 0, let's go with that. So let's say if we do fold left plus 0, we could write this as a for loop. Let's just go. It's a little bit tedious. Anyway, let's go for each. Something like this, anyway. So cum equals something like that. I think I got that right. Yeah, I got that right. So this is what fold left basically represents. And let's generalize a little bit. So let's go that. Generalize a little bit. So this is, when we see fold left, think about it like this. If you're coming from something like JavaScript, think about it exactly like this. We have an accumulator, which is the initial value. Then we go through each element, and we run our function with the current value of the accumulator. So we can do something with the current value of the accumulator, something with the element that we're going through, and then we assign that back to the accumulator. So we're just going through and we're just running a function for everything in the list. So that, fold left, if you've thought about fold left like this, it's actually right. Fold left is a for loop. Think about fold left as for loop. Don't think about fold right as for loop. Fold right is constructor replacement. That's really important. Fold left, think about as a for loop. It just is a for loop. Going through every element, running a function, taking the result. So, I mean, this will be the same. So let's say we got 1 cons 2 cons nil. Our for loop would look like we run the function. Oh, sorry, our initial value will be 0. Then we run our function, which will, let's say it's plus again, so 0 plus 1, which will be 1. And then we say 1 plus 2. Then we say 3, right? Go back 3, and that'll be it. So it's just a for loop. So we start off with 0, run our function over it with the element, run our function over it with another element, then we get back a result. Just a for loop. That's the important thing about fold left. And fold left you can actually implement in terms of fold right. So fold right can implement fold left. And that's an important thing to understand as well. So fold right is kind of like the essence of a list. It's the really important function. Everything you can do with a list you can use fold right for. So fold right is an important function. It's like the essence of a list. It's everything you can do with a list you can do with a fold right. Fold left is just a for loop, so it's just something that's convenient. There's nothing essential about for loops. It's just something that we sometimes use in Haskell. Sometimes we use a for loop. Sometimes we use a for loop. We just call it fold left. But yeah, the essence is the constructors and constructor replacement. Really important to think about. Fold right is constructor replacement. Fold left is sometimes useful, not essential, but sometimes useful. It's a for loop. hopefully that clears up some things, especially, I know that like JavaScript, when they call things fold right, fold left, bit confusing. Thank you for the follow. Hopefully you're getting something from this. This is like, if you're gonna get anything from doing like the first couple modules in the FP course, this is the one thing to get. Constructor replacement and for loops, really important. Cool, so we're going to practice mainly fold right. We're not going to do too much with fold left because fold left is just, a convenient thing to have. It's not essential. So we're going to practice a lot on fold right in this list module. We're going to implement, so we're going to implement, let's think of, let me think about this. There's a couple ways to do head or. There's a couple ways. So I'm just going to think about what is the... I think we'll start off with doing pattern matching. We'll start off with that. We'll start off with pattern matching to implement this head or function. Does anybody want to guess how we would use pattern matching to implement this? So we've got an X, we've got an A, and we've got X's, right? So pattern matching, we can pattern match on X's, and we have two cases for X's, right? We got nil, or we got cons. So those are the two cases. Let's just make sure we got the syntax right. We should do, yeah. So we've got two holes. Cool. So remember, head or on nil returns the first thing. So this is very similar to what we wrote with our question mark optional thing. Two question marks. So we've got like a value and we've got like a like the default value to use. So we could use that. Oh, sorry, we're basically doing something like that. So we return back the A, right? But then here we have head or, and remember, like it's very similar. If you think about it, you can think of optional as a list, but that has only one element. It doesn't have the recursive part. We have list, which is, it's either nil or it's a head and a tail. If you just get rid of the tail part, it's the same data type. So, and we're implementing this function basically as if list is an optional. So, because we only really, if you look at this function, we only care about the first argument. We don't ever care about the tail. We just care that it's either cons or it's nil. We don't actually care what the tail is. So, because we don't care about what the tail is, we can get rid of that. And also remember that in our case where we had full, we put an underscore here to say that we don't care about the default value. Do the same there. And so that means the implementation must be, if we go over to our thing, hole-driven development means we need to give back an A. Remember to do, this identifier has type A, so therefore here, we need to replace this with something that has an A to make it compile. Here we've only got an A, we've only got one A in scope because we did this, we replaced this with underscore, only one A in scope, therefore implementation must be X. Hole-driven development, got us there. So that's one implementation. Using pattern matching, we can implement this function. Another way we can implement it is using fold right, using our constructor replacement. So whenever you see pattern matching, usually you can replace it with constructor replacement, fold right. So we'll have a go at that. That is the better solution. So you can come up with this. You can implement the exercise like this, but the better way to take this exercise is to try and use fold right to implement this. So I'm going to put in two holes, right? So what this is saying, right? We want to use fold right, and remember, fold right takes what we want to replace our cons with, and what we want to replace our nil with, and then takes a list. This is what we want to replace cons with, that's what we want to replace nil with. I don't know at the moment. I don't know the implementation, right? This is Haskell. I'm writing Haskell. I'm going through something called the FP course, which is the beginner Haskell stuff. So I'm just teaching the beginning of Haskell stuff. We only got into like the first real module at the moment. Australian English. Yeah, it is Haskell. Cool, so we don't know what to replace cons with, we don't know what to replace nil with, but we know we want to replace it in this X's, because that's the only thing we want to, that we have, that's the only list we got, right? And we know we want to use fold right, because I've said so. We want to use fold right because I said so, so therefore we have to use it over X's. So, replace cons with something, replace to do with something. So let's If we reload this, we will see that we've got two holes. We have a hole here, which is that we've got a function that takes two A's and gives us back an A. And remember, I'm being sloppy with my, when I say it takes two A's, it actually is a function that takes one A, returns another function that takes another A. So it ends up taking two A's, but it doesn't really. And here's the things we have in scope. And for this case, we have to do 2. It needs an A. How can we get an A? Well, there's really only one A that we have in scope. We've got this, I mean, we've got a list here. We've got a list of A's. But we're already using that list of A's. So let's ignore that. We've got this thing. So let's say if we replace nil with A, what would happen in these cases? If we replace nil with A, so we went through our list and replaced nil with A, what would we get back? This is our A. Replace nil with 3. Get back 3. So that makes sense to me. We've replaced nil with 3. We get back 3. So I think just doing hole driven development, you get there. You say fold right, replace the nil with our default value. So in the case that we give this fold right a nil, we get back the default value. That makes sense to me. So our other hole that we have is to do 1 here. So to do 1. And so if we look at this, right? Let's look at it like this. So fold right. Let's go 1, 2. So let's say this. So fold right, remember constructor replacement, we want to replace nil. So we're taking this list, nil, and we want to replace nil with A. So that becomes A. So that makes sense to me, right? So in this case, we want to fold right, we want to replace 1, 2, 3, nil. But we're replacing nil with A. Oh, I've got a nil up here. Let me, this 3 is too much. Let's get rid of that. So we have this thing, right? And we're replacing this thing with F. And in this, we've got head all, right? So we want to get back. These courses are great. I'm struggling in transitioning from exercising simple command line tools to designing real software. Right. Any recommendations and resource simple open source projects? Xmonad is something that I found really useful to look at when I was first starting with Haskell. Xmonad is a fairly small library, but it's really useful. It's like super practical. I use it. I mean, I'm not using it at the moment. Well, I actually am. Outside of the window that I'm twitching in, I'm using Xmonad. Where's the source for this? It's on GitHub now. They moved to GitHub. Yeah, here we go. Read through the Xmonad source. It's pretty good. I mean, there's some problems with it, but I mean, overall, like, I mean, it will show you how to make a useful app, even if it's not the, I don't know, even if it's not the most well architected. It's pretty good, pretty good app to look into. There's something. Where is it? Core, I think it is. So if you look at xmonad.core, like, it's only a few. I think it's like 1,000 lines or something. But basically, you got this one big data structure, and then you got functions that work over that data structure. It's a really good way of learning about how to structure a Haskell app. So you basically got this one big data type that includes all of its state in that, and so you can kind of see how you would use it. And uses things like monad reader, monad state. So it uses something called MTL. This is MTL. So you learn MTL to implement this. I found this really useful when I was starting Haskell. I mean, of course, I benefit from it because I actually use Xmonad as well. But yeah, this is useful. I'd recommend looking into this. I don't really have. I mean, there's Pandoc as well. I've looked into Pandoc when I first started Haskell. I played around with Pandoc a bit, learned how it works. There's a couple of small Haskell libraries or executables that you can go through and have a look at. Pandoc, Xmonad are the two things that come off the top of my head. There's languages as well, like there's PureScript, Idris. You can look into the implementation of those, although they're kind of tricky. I think Xmonad is probably the best place to start. Maybe go to Pandoc after that, and then maybe once you get more comfortable with it, go on to something like PureScript. PureScript is not massive. There's some details, like there's some parts about it that are a little bit intense, but I'd probably go through that. Start off with xmonad, go something like pandoc, and then go through to something like purescript. I mean, that's kind of the general direction that I went. I mean, it took me many years, but that's kind of the general direction I went in. Cool, so back to fold right. Fold right, replace nil with A. Fold right, replace cons with F. Replace nil with A. So if you look at our example up here, in the case that we have nil, we'll just give back the value. If we have an element though, give back the element. So give back the head. So if you think about this, what could we replace? What function could we write in here? What function could we write here that would just give back that? So remember that this is the same as f that. Right, so what could we use, what could we say, what function could we write as f that just gives back the first argument, right? Well, we could write a function, let's write that function. So in this case, you probably can hopefully see that this is what fold right becomes. When you write fold right fa for a list that's 1 and 2, then it becomes this. This is what fold right means. Replace cons with f. And so if we want to say that returns 1, then f is just a function that returns its first argument, right? So remember f. So if we want to say that this whole expression equals 1, then f is just returning the first argument, and it's ignoring the second one, right? It's ignoring its second argument, or ignoring that part of it. So that means that we've given an x and its second argument, because we're going to ignore it, we can say underscore. That's the implementation. Well, that is a implementation anyway. We're going to do a little bit more to it to make it a little bit nicer, but that is an implementation of this function. Take in the element, return the element. So if we have an element, just return that, and that's the result. So that'll happen here. If you've got head or 3 and then 1, 2, nil, run the function on the replace the cons with this function here. Sorry, replace the cons with a function that only just gives back 1. Nice video series called Haskell at Work. Yeah, that's a new series that's come out. Yeah, that looks really good. I haven't watched too much of it, but yeah, that looks really good. I think it's for people that are a little bit familiar with Haskell. But yeah, it's got some really good stuff on there. So we have a function that just returns the first argument. There's actually a function already called const. So const 1, 2, const 1, true, like const just returns its first argument. You give it two values, it will just return the first value. And so what we have done is re-implemented const. Yeah, k combinator. If you're familiar with SK combinators, it's k, which is const, the constant function. So what we did is re-implemented the constant function. So we can just replace it with constant. That's a little bit more readable to me. When you start putting, like, I know when you're starting off with Haskell, it's less readable. Like this is probably more readable to people that have started doing Haskell. But after a while, this is much more readable, and I'll tell you why. Well, one of the reasons why. One of the reasons is that when you start introducing variables here, I have to think about where is that variable used. And so even though this is a small function, I have to think about what's the scope of this x? Where is x going to be used? How many times is x going to be used? Is it going to be used 1 time, 2 times, 3 times, 10 times? I don't know how many times x is going to be used as an identifier to be referenced. It could theoretically even be used 0 times. Like I could do that. I could make that mistake. So introducing, explicitly writing out functions can actually be detrimental, even though it might make sense to you at the moment, and that's fine. Like if you just wanna write lambdas out and write these functions yourself, that's fine. But eventually, you might have to trust me a little bit But this is much more readable in the end. Because you don't have to count how many times identifiers are used. You don't have to worry about scoping. All you have to do is just look at this. And to me, this is quicker for me to read. This const is quicker for me to read than that. That is a little bit slower for me to read. So eventually you do build up a way to read these sort of things. If this is not readable to you at the moment, there is you can use my Twitch bot. Let me show it. Let me show my Twitch bot. If this is not readable, if you're struggling to read this sort of stuff, my bot can help you out a little bit. I'm not even logged in. I won't be able to chat, I don't think. Here, I'll just. Don't even know if I can. I think my screen's too small for this to. Oh, there we go. All right. So hopefully, don't get too constructed by my face being there 1,000 times. I think it's point. What is it? I'm trying to think of it. There's a command called point. I don't think it's called pointless, is it? So pointless. I think it's like this. There we go. Okay. Wish I could make. If I pop this out, here we go. Let me try that again. So if I type in PL, there we go. Ah, see, this is the thing where the chat doesn't work. Hang on. There we go. Welcome to the chat room. That's what I'm waiting for. Okay, try again. PL. One more time. Okay, cool. So if you are confused by whoops. If you're confused by when you see things like this, if you're confused, or if you are, if you're confused by how to get to something that's that looks like that, then you can use this pointless function, which will take this function, this one where you actually have variables, and it will replace it with one that doesn't. And then there should be the reverse, which is point full, I think it is, so PF. So I should be able to say PF const. Oh, what's the point full const? There we go. Point. So if you type in, if you see me write something that looks a bit confusing, you can use this point full function, and it'll expand it out. So if you're struggling from going from something where you've written out a lambda and you don't know how to improve it, you can use point full, and sometimes. Oh, sorry, yeah, you can use pointless, PL, column PL, and then this, and that'll give you const. It'll say const. If you want to go the other direction, if I've written something that you can't understand, try writing point full const, and it'll give you back this. So it's a bot that can go in both directions. It can tell you how to improve your code and also how to read my code if you're struggling with that. But for me, and eventually for you, if you keep going with Haskell, you will get more familiar with using this, and this will become more readable than that. You might have to trust me a little bit on that, but that's a very common thing. If you get really good at Haskell, it becomes quicker to read this. What we call the point-free version, and so pointless is kind of like a play on words there. Pointless, point-free. So we call this the point-free version, and the other version we call the point-full version. This is the point-full version. There's some category theory or something about what a point is. I don't really understand it. All I know is that lambdas can have points or something. You can take the points out. Points are the arguments. Cool. So that's one refactoring you can do. Replace the lambda with a function that already exists. That's really useful. Constant function. Cool. One more refactoring we can do, which is we have the same things on the left-hand side here. We've got a and x's, and we've got the same thing on the right-hand side. When you see, in Haskell, the equal sign really means equal. And so if you have, if you think about in mathematics, if you have f of a equals g of a, if you think about this, that just means f equals g. Those are the same thing. If you're saying given a function that takes an argument is the same as running a function with an argument on another function, then really what you're saying is that the functions are equal. And this follows for here. We're saying a function here, our function head or, takes in an a and x's, and it equals a and x's over this function. So really what we can do is just drop that and drop that. And because Haskell equals really means equals, that's the same. So head or is fold right const. It took us a couple steps to get there. And there's a couple of different ways we can implement it, but this is, I think, a really good implementation. Head or is fold right const. Is anybody confused by that? It took us a couple of steps to get there, but we got there in the end. Is anybody confused by how fold right can give back the head or the default value for us? Yeah, here we go. Let me just demonstrate that I'm not lying. This actually does work. And also, what's interesting is that if you tried using a for loop, you couldn't implement this using a for loop because you can't do a for loop over infinity. If you see infinity, don't think fold left, because fold left represents for loop. Think about how in an imperative language, if you try and write a for loop over an infinite list, or like if you try and write for I is 0, I until infinity, think about what that's going to do. So that rules out, because we see this property here. Actually, I should talk about what property is. A property here means that whenever we see x, when we see prop, when we see x, that means like for all x. So we could generate, it doesn't matter what x is, we could generate a million different x's, and this property always holds. So doesn't matter what x is, x could be that, but head or infinity always equals 0. So it doesn't matter what x is, it always equals 0 when you do head or with infinity. But also here, if you do x, if you do x head or nil, so if nil is on the right hand side, it always equals the first argument, so it always equals x. So it doesn't matter what x is here, it always equals x. So if you're thinking about fold left infinity would be an infinite loop. So obviously the implementation of head or can't use fold left. That's just something to think about. Dislike this part where parameters are dropped most of the time. Much hard to understand what's going on in the first read. Yeah, well, I mean, like I was saying before, where if you put in the parameters, I now have to think about where these parameters are used. How many times is a used? How many times is x used? It does, eventually with enough practice, it does get easier to read this. It gets a lot easier to read this. I've seen, like, when I teach people Haskell, like the people in my classes, they've been going on for about 6 months or so. It seems like they prefer this because they automatically start writing this. They go to write that and then they get down to that. And not because I tell them to, but just because that's what they find easier to read now. So after about 6 months of practice, they've got it down that this is easy to read. It does take a while to get to practice it, but you do get there. Cool, so product the elements of a list. How would we implement this? What would we replace? So it looks like product nil. So if we're thinking about constructor replacement, that's kind of the default thing to think about when we're working with lists. I think ADA reduction it decreases overhead. I do it in TypeScript all the time. Yeah. That's my experience as well. So okay, let's talk about product. So nil. If we want to replace, what would when we think about list, we think about constructor replacement by default. If we replace, what can we replace nil with to make a product? Well, 1 is kind of like the default element, default way to think about products. But thinking about constructor replacement, if we have this list, how can we make this list represent product? So cons nil. So It looks like we've already been given the answer for what nil should be replaced with. Should be replaced with 1. To do a product, what would we replace the cons elements with? What would, well, sorry, the cons, what would we replace the cons function with? To do a product over a list, what do you replace cons with? Product from a list, replace cons with something to make a product. What are each of these doing? So if we've got 1, 2, 3, and we want to do product, what do we do with 1, 2, and 3 to get to 6? I mean, we could add them actually, that's a bad example. That's a bad one. 1, 2, 3, 4, how do we get to 24? Multiplication, exactly. We got the answer. It's multiplication. So if you multiply 1 times 2 times 3 times 4, we'll get to 24, right? Instead of 1, how about multiplicative identity and solve some at the same time? Yeah. Yes. You are getting onto monoids. Yeah. We'll get there eventually, but yeah, monoids. Yeah, get it for free, exactly. Monoids is the way to do that, exactly. Yeah, you're completely right. Monoids is the way. I don't think, actually it's not even in this thing, but yeah, monoid is the thing to look up to be able to do that, and that is a very common thing to do in Haskell. Absolutely. Okay, so we want to multiply these things together, right? Okay, so let's say times. Yeah, let's go with that. So that would look like 1 times 2 times 3 times 1 in this case here. Or if we went with 4 to get to 24. Times 4. Cool. So this is what we kind of like. This is kind of what we want the expression to look like. People in the chat are pointing out that want to look a little bit like this. We can put this because what we've been saying is that, you know, multiplicative identity. If we look at the 0 element or the identity element of this thing, we can just say multiply by 1 is the same as the original value. So, you know, x times 1 is the same as x. And that's because, yeah, there's some math behind that. So it's kind of like a neutral element, yeah. Neutral element, 0 identity, different names for it. Yeah, so if we treat nil as like the 0 or the identity element, we can run the operation multiplication with that, and we'll get back to the same answer. So what we can say is fold right multiplication 1. I'll leave that in. So product 1, 2, 3, 4, nil. Should go back 24. So what that's done is replace cons with multiplication, replace nil with 1. So that's a pretty easy way to think about it, right? It's just go through there, cons becomes multiplication, nil becomes 1, so it's the same thing. And that's what we get out. So what we really wanted to do is just multiply them all together, and that's what we've done. Easy. So what would sum be? People probably can come up with the answer for this. So this one doesn't really show, like here it showed that nil should equal 1, right? So what should cons and nil equal here? Cons nil. So nil needs to be an integer. What can we use for that? And cons needs to be a way of taking two integers and get back an integer. So if we want to sum them up, what operation would we use to sum things up? So right, nil would be 0. Nil would be 0 because 1 plus 0 is 1. So, you know, we want something that if we replace nil, we want it to kind of not count. We want it to not go towards the solution. So plus 0 would mean that that we've reached the end of the list, and that'll be the final thing there. And exactly, yeah, if we replace cons with plus, arrive late, are the course modules public? Yes. I think what you're looking for is, what you're asking about is this, Data61 FP course. If you go to GitHub, source course, and we are implementing at the moment, we're running, we're using list. Work on list. Thanks for the link, awesome, thank you. That's exactly it. So Data61 FP course, we are going through this. So this is what I do at work. I go through this. I usually go a lot slower and iterate a lot more on it. But yeah, we're just going through these modules. We've done it in the right order so far. We've gone through just some syntax, then we went through validation, exactly one, optional, and now we're up to the list. So we'll go with list. We'll try and get through a big chunk of list. Sum is fold right plus, so replace cons with plus and replace nil with 0. Easy. Okay. Now length. If we want to take so we've got a list. 1, 2, 3, nil, right? Obviously the length of this list is 3, right? What could we replace nil with? Nil is a list of length 0, right? So I think we got our answer for nil. Replace nil with 0, because that's the length of the list, right? What do we replace cons with though? What can we replace cons with so that we get 3 at the end here? Anybody want to describe in English what you would do with cons to make it so that we got 3 at the end here? So thinking about it like this, right? So actually, there's more than one implementation there, but anyway. So 1, 2, 3. What can we replace f with so that we get a 3 here? Add 1. Exactly. Just for every element, so every time we see an f, we just add 1. Just add 1. Exactly, that's the right way to think about it. So fold right, so cons 0. So every time, so remember that the first argument to fold right, remember it's replacing cons. So what do we do with the element? Because it's cons, right? So we got the element here. What do we do with the element? Well, we don't actually need the element because we're only counting how many elements there are. We're counting how many times we've consed. Really, that's what we're doing. So we don't actually care about the what that element is, what each element is. We don't actually care. So we can just replace that with underscore. So this is fold right. Take the just ignore the elements. Ignore the element. Get the and just do +1 to for every result. And so remember that I said that if you see we could write it like 1 plus b, right? That's the same. And remember that I said that if you see something on the right hand side, you can get rid of it. So that's the same function, and also because we're just ignoring it. Just ignoring the first thing, so what we could do is flip const. Is that it? Flip. I'm gonna have to, let me run point three on that. I'm struggling to think of it. It should be obvious to me, but I'm struggling to think of it right now. Const +1. Oh, okay, yeah. Yeah, that makes sense. Okay, cool. So that's the same function. So const just means, you know, give back this thing. Give back this thing. So it'll ignore the element, so we'll put in the element here, and then it'll give back a function that's +1, so then we give it back, so then we give it run, you know, b, we'll give it b, it does b +1. So that's how it works. So that is length, so we can say length of 1, 2, 3, nil. There we go. So it doesn't matter what the elements are, we'll always get back 3, because what it's doing is just counting how many conses there are. That's all it really is doing. It's just depending on the constructors. It does not depend on the elements. So that's also why we have an A there. It doesn't use that element at all. It does not use that A. Just counts something about the, you can reason about this actually. You can say, because we're saying list of A and we're giving back an int, the only thing that this function can do is do something with the constructors. That's the only thing it really knows about this list, this input thing. It only knows about the constructors because we've got this A, so we don't know anything about A. We're saying for all A, so we don't know that it's an int, we don't know if it's a bool, we don't know if it's a string, we don't know anything about that A. All we know is that we've got a list. So reasoning, we can actually reason about this type signature and say that the only thing that this function does is produce an int based on the structure of the list, not on the elements inside the list. So that's something interesting. That's a topic called parametricity. We'll go on and on about parametricity later on, but we know that this function only does something with the structure. Cool, so now let's write map. So defaulting to fold right as usual. So map takes a function and takes a list. On that list we want to do fold right just by default. Let's just guess that we want to do fold right on it. It's a good way to think about it by default, fold right. So nil, if you're mapping and you want to replace nil with something, so let's say 1 cons, 2 cons, 3 cons, nil. Map f of nil is the same as nil, right? And in this case, what are we constructing up from a list? We're taking a list and we want to construct something. We want to construct a new list. So the result of this must be nil. When we're folding over a list and we're trying to reconstruct a list, but the nil stays the nil, must be nil. Must be nil. When you do a fold right, second item must be nil. So we're left with one thing, which is a function called cons. We need to replace cons with a function that takes an A and a list of B and then produces a new list of Bs, right? So it's a function that takes an A and a list of Bs and then does something. It produces a list of Bs. So we need to create a list of Bs, and here's the things that we have in, here's the bindings that we have in scope. So we've got our Bs, list of Bs, and we've got A, and we've got a function, A to B. So if you look at this, how do we create a list of B? Well, there's two ways to do it. We can use nil or we could use cons. We could chuck nil in there, but then if we went to run this, fold right would mean like we'd always just get nil. So it can't be nil. We don't want to put nil in there. That doesn't seem very useful. So we want to use this list of Bs in some way. So we could just say list of Bs, but then that would also just be that'll be nil because we go through each element, and if we're not using the element, then well we'll just get back what we put in. So Bs will just be nil in the end. If we just replace this with Bs, we could do fold right. Sorry, we could do map +1, 1, 2, 3. And we'd always get back nil. This is just a pretty printed version of nil. So we'd always just get back nil. So we need to do something with this Bs. We need to do something with this. We need to do something with this to make it do something. So if we had a function f1, f2, f3 nil, what can we do with f in this element? And we have these bindings in scope. Hang on, I have these. These things in scope. And if you think about it like this, remember it's constructor replacement, replacing cons with something. Hopefully you can go between these two. You can read the similarities between this, how we're replacing cons with f. So this is let's call it g. Okay, g. Replacing cons with g. What do we have in scope when we go to implement g? We have, well, we got the element, which is that. We've got this element 3. We've got a function that takes our 3, our int, to some other b. And then we've got a list of b's. So if you combine these all together and you say, well, okay, I obviously need to replace it with cons something, because in the end I want to say, let's say our function is +1. So really what we want to say is 1 plus 1. And we want to cons it on with 2 plus 1, cons 3 plus 1 nil. So if you look at this, if you look at the similarities here, we've got this list and we've got this, what we want it to be. This was the original list and this is what we want it to be. If you kind of look at the similarities here, then you see that G must do the consing and also do the +1, so run our function. So it does that. Whoops, not G. Does that. So that's kind of how you think of it. So you can think of it as, replacing constructors, replace it with G. What would G look like? Would it look like something that would, run our function that we pass in over each element and then cons it back on. So that's what. So if you kind of think of it like that, run the function, cons it back on. So we've got our function fa. So run our function over the element, cons it back on to our b's. And that's map. So now we can map +1 over every element. So basically what we're doing is we're deconstructing the list using a fold right to do constructor replacement. So we're deconstructing the list, then we're reconstructing it back up. So reconstructing it using similar constructors, using the same, so we're replacing cons with cons that's slightly different. Cons is not just cons. Cons also runs the function over the element. Relationship between G and cons here may be clear if you first rewrite. Yeah, if you rewrite, okay, cool, yeah, I can do that. So, there you go. So what you can do is put it into prefix form. This is, remember, operators can be infix, meaning they can go in between two arguments, or they can go prefix. And so what I've done is I've just moved it into prefix here. And then I've said, okay, well, I'm going to replace it with G, because I'm going to do a fold right, and I'm going to give the first argument to fold right. Let's say I give it G. That means I've replaced, in this list, I replaced all the cons with G, so it looks exactly like that. So it really is just replacing this with G. Each one of these cons here just gets replaced with G. And then in my actual example, in this map example, so under map, I want to run a function over every element, but then I also want to rebuild the list back up. So it looks something like that. And this is an example of using +1. So go through the list, replace cons with some sort of function. What would our function look like? Well, it would look like running our function. If it's +1, it looks like that. But it would look like running our function over every element and then reconstructing the list back up. So that's what we've done. Replace nil with nil, replace cons with cons, but also cons that runs the function over the first argument. So that's how you can read it. And so we can also drop it from here. So I think that should be the same. Is that right? Yeah, cool. So remember that if you see something on the left-hand side that's equal to the right-hand side, then you just drop it from both. So there we go. And you could also run, if you run this, I could run point free over this. And let me do that real quick, but I would not use it. So let me run point free on our current implementation. So if you, whoops, well, someone's got a weird username in there and just did something weird. Okay, so you could write it, so profunctobot just told me I could write it like cons compose with f. Actually, that's not that bad. I was about to say I wouldn't use it, I wouldn't write like that, but I actually would. That's actually fine. Yeah, that's actually fine. Sometimes point3 comes up with things that I wouldn't use. And usually the way that I work is if I derive it in my head really quickly, I wrote it like that, but for some reason I didn't derive it really quickly like that, but yeah, I would write it like that, that's fine. This language is Haskell. This language is Haskell. Cool, so that's map. Let's go on to filter. I'm just going through this real quick. Sorry if anyone's getting a little bit left behind. If you've got any questions though, please ask questions. I'm happy to slow down and answer any questions. I'm conflicted because I think some of my audience is, you know, quite familiar with Haskell and some of it are quite new to Haskell. So I don't know. I'm kind of going a little bit slow in some parts, going a little bit fast in some parts. Going slow, particularly in the parts that I think are really, really important. But please, if you have questions, ask me, and also, you know, take the time to do this course by yourself. Hopefully I'm not giving away too many answers. Hopefully you'll forget this if you actually go to implement it yourself. Okay, so filter, remember, you know, by convention or by default, if you've got a list, think about fold right to begin with. So I'm going to do fold right. So we've got a function and want to do fold right, cons, nil, what we will replace cons with, what we will replace nil with. I don't care about syntax. How do I stay reasonable coding in this syntax? I don't care about syntax. Syntax is not important to me. It's like the lowest priority in the world in terms of me writing programs. I really don't care about syntax. You can give me whatever program you want. I will not care about syntax. There's a lot of things I do care about, but syntax is really low on the list. So we're going to replace cons with a function that takes an A and a list of A and gives back a list of A. And nil, we need to replace with a list of A. So filter is going to take a list and give us back a list. What do we do with filter on a nil? Well, give back a nil. I think that makes sense to everyone. Filtering nil is the same as nil. Doesn't matter how many elements are in the list. There's actually no other right answer. We can't actually just construct a list here. So it has to be nil. Okay, so fold right, cons. Okay, cool. So now we've got one thing to implement, cons. So if we went to filter, went to fold right, so 1, 2, 3, nil. Just joking, Jesus. Everyone, calm down. Calm down. Okay, so 1, 2, 3. Okay, so let's say we want to filter this. What can we replace cons with to filter this? So let's write it like this. Remember, 1, it's equal to 1. Like if we're replacing cons with a function f, then it looks like this: f3 nil. It's a little bit confusing again because we've got this, because we've got f in scope. So what we want to do is say, like, well, if for every g, right, we want to say, well, if f for that, right, we've got a predicate, right? Predicate. So let's call it p, predicate. So we've got this predicate function, right? So we want to run our predicate over every, every element. And then what do we want to do if we run the predicate over it? Well, we want to change whether we cons the element back on or we don't, right? So probably might make more sense if we do this. Okay, so to do is a list of A, and we have our predicate here, which is A to bool. So that's how we run our predicate, right? So we can give predicate A. So then we get back a bool. So we can say if, right? So if P A, So hopefully that makes a little bit of sense. So now we've got two holes. We've got two things to fill in. So we need to fill in the true case, fill in the false case. To do 1 is the true, to do 2 is the false. And so they're both list of A. So we just need to fill in a list of A. So what will we do if the predicate holds for A, right? So if the predicate holds for this, for every element, so we're going through every cons, replacing with this function. So A in the first case is 1, A's is, you know, this computation, the rest of the computation. So the predicate we run on the element, then what do we do? Well, in this case, right, if the predicate holds for 1, let's say the predicate is constant true. So we should get back out the same list, right? We should get back out. So if we always are true, if it's always true for every element, it should get back out the same list. So what we want to do is cons are back on, right? We want to reconstruct the list that we deconstructed. So fold right is deconstructing, right? So we're deconstructing the list, going through every element, we're going through cons and we're going through nil and we're deconstructing it down, replacing it with a function. If we want to reconstruct back up, we can replace it with the same function. So we can actually let me write the identity function real quick. So this is list of A to list of A, identity, fold right. So imagine if you took fold right and you replaced cons with cons and you replaced nil with nil. So this is, you know, go through every cons, replace it with cons, go through every nil, there's only ever one nil on the list, but replace nil with nil. So I should be able to reload that, well. So identity, 1, 2, 3. So if you're using fold right and you replace the constructors with the original constructors, you get back the same thing. So that's just something you can use. So you can use that here when you're saying that if predicate is always true, then, you know, reconstruct up exactly the same list that we created. So A cons 8. And so now we've got one hole left, which is that if the predicate is false, what do? We just don't cons on that element. We don't want that element anymore, so just use A's. So that's filter. Let's try some of the examples up here. So filter even. And there we go. Hopefully that makes a little bit of sense. Cool, it does. At least to one person. That's good. It's good when things make sense to more than just me. Cool. Okay, now this one's a good one. We want to fold right simplifies a lot of things. It definitely does. Yeah. I mean, we could do like pattern matching and things like that, but I mean, fold right. Just think about things as constructor replacement. It's good. So list append. I don't know how much we're gonna get through. Let's. I don't think we ought to get through everything today. Let's try and get through. There's some cool ones here, so let's get through these ones. So list append. So let's say we have a list. Got a list and we want to replace. I don't want to give the answer away too much. You know, appending to lists. We append to lists. This is Haskell. Yeah, that's right. This is Haskell, and we're going through something called the FP course. Used to be called the NICTA course. Data61 / FP course. Used to be called the NICTA course, and I teach this at work a bit. And so I'm just showing how I teach it. I'm doing it really quickly, but I'm just showing how I teach it. Some of the terminology I use and some of the I don't know, some of the explanations I give to implement this function, to implement, you know, these functions. So I teach this at work. It's a really good course. It used to be called the NICTA course. Now it's called kind of like the Data61 course. Maybe I don't know. It's maintained by these people, the Queensland Functional Programming Lab now. And so these people go around around Australia teaching functional programming, and they use this course to teach functional programming. So there's this one. They also teach it's the QFPL Applied FP course. So they teach two courses. They travel around Australia teaching two courses. Applied FP, which is kind of like making web servers and making websites and stuff using Haskell. But this one's kind of like the basic one that we're going through, which is the basic, here's how data structures work, here's how the syntax works, here's how Haskell works, basically. So the fundamentals of Haskell they teach, and they go around Australia. So they taught a class in Sydney a couple of weeks ago. They taught it to a heap of people in Sydney that I work with. I work for a company called Atlassian. There's a heap of people in Sydney that work at Atlassian. They taught those people in Sydney for me, which was awesome. and I've been teaching quite a few people in San Francisco, so about 10 people. So I've been using this FP course to teach people Haskell in San Francisco, and it's a really good course. They've gotten really far. It's absolutely awesome. I highly recommend going through this course if you're interested in Haskell. Use this course. It's really good. Never understood map in pure functional languages. Right. So we did map just before. Really, what map is going through our list, replacing every time that we see cons. I might have to go through a list a little bit. So list has got basically there's two ways to make a list. There's cons and there's nil. Those are the two ways to make a list. Nil represents empty list, and cons represents we call this cons here. This operation, this colon dot. We call that's pronounced cons. And cons represents an element in another list. So we say head and tail. That's usually how we call them, or how we pronounce them. So cons has a head and it has a tail. And so what we've done here is, if you look at just this expression here, so nil is a list that's got 0 elements. If you look at this expression here, we've got a list that has 3 as the first element, and that's it. It's just got 1 element in it. So it's a linked list. It's exactly a linked list, exactly. And this is another list here. So just this expression is a list that's 2 and 3 in the list. And if you look at this expression, it's 3. It's got 1, 2, and 3 in a list. So each time we're like adding on a new head, we can say it's a new head, and this is the tail. So for this list here, 3 is the tail. Yeah, it's a functional linked list, exactly. Thanks for the follow. So this is, yeah, so that represents a list that's got 3 elements in it. So 1, 2, and 3. Map is just running that function over every element in that list. That's all it does. So if you have map, yeah, here we go. If I have this list 1, 2, and 3, map f 1, 2, and 3. That's the same as maybe I'll swap that. There we go. So every time we see an element, we replace it with. It's for each. It's basically for each, but what we're doing is we're creating a new list at the end. It's kind of like for each. It's kind of like for each, but not quite. What we're doing is creating a new list at the end. So we go through every element, and we just run the function over it, and we get back a new list. So this actually represents a new list. So if we did, here's one example I had. Oh, thanks for the follow. So yeah, for each kind of makes side effects. It's mainly used for side effects. So it's kind of like that, but it's not really used for side effects. It's for creating a new list. So go through every element in a list and create a new list. An immutable for each, you can think of it kind of like that. It's not for side effects. It's for running a function. I mean, we don't really use side effects. Well, we don't use side effects in Haskell. It's just running a function over every element and getting back a new list. So get a list of 1, 2, 3. Run the function over every element and get back a new list that is, that. So if we did, an example would be plus 1, 1, 2, 3, nil. So this will just go through every element, run +1, and we get back a new list. So hopefully that explains map. Cool. So appending. How can we represent appending? If we do, remember that I wrote the identity thing before. Identity is folder right, replacing cons with cons, replacing nil with nil. That is identity. So if you look at this function, right? If you look at appending, 1, 2, 3 nil plus 4, 5, 6 nil. So if you look at the similarities between this and that, if you look at the similarities, I mean the syntax is slightly like this is pretty printed, right? This is pretty printed. But if you go through and you look at the similarities, what's the difference between this list and these two? Like what's been done to these two lists? So I'll write it out so it's not pre-printed. So this, right? So the result is that. So if you look at these two things, right? So plus plus, if you get rid of the plus plus, and you kind of look at this, what is happening between these two things? Anybody want to point out what's happening to either of these functions so that we can get this? So we're concatenating them, right? We are concatenating them. But what's if you took one of these lists, what would you do to the other one to make it the same? Well, there's something going on here. Like the plus plus is really only doing one thing. If you go through here and you look at nil, what's happened to the nil? What's happened to nil between these two? So you got 1, 2, 3, nil. So this is similar, right? It starts off the same. 1, 2, 3, nil. 1, 2, 3 starts off the same. But something's happened to the nil. See, notice that nil has become that. Nil has become the second list. That's interesting, right? Nil gets replaced with, yeah. Well, yeah, you're kind of getting there. You're getting towards there, but you need to flip it, right? So nil is becoming this. Becoming the second list. So what we're really doing is, remember, if you're doing constructor replacement, you got cons, and you got nil. Replace nil with the second list. Does that make some sense? If you're doing constructor replacement, you got cons and you got nil. Do constructor replacement on this first list. What if we replace nil with that? Then you would end up with this. Does everyone agree with that? Replace nil with that, you get this. So fold right, if we replace cons with cons, because the cons is going to remain here, but what we're going to do is replace nil with our second thing, with our second list. So here, concat is really just replacing the nil, replace nil with the second list. And we said flip before. Whoops. Did I do that wrong? Oh, should be able to do that. Cool. And do I get the same result? I do. There we go. So that's the implementation for concat. It's a really cool implementation. It's basically replace nil with our second list. Replace nil with our second list, and that's concat. All you're doing is going through the list. Whenever you see nil, at the end of the list, replace it with the second list. That's it. That's what concat is. Yeah, flip. Exactly. Flip will flip. Yeah, I thought that's what you're getting at. Yeah, flip. Cool. So hopefully people get that. Now we're going to go on to flatten. So we're going to have a list of lists. So this is a list of lists. So you can see there's a list on the outside, and then each element of the list is an all list that's got elements. So we're going to do fold right again. Just by default, we just do fold right. Okay, so what we have, we need to implement nil, and nil is going to give us back a list. So if you've got an empty list of lists, empty list of lists becomes an empty list, right? Ah, already got it. Awesome. Well done, you've already got it. That's awesome. I work on this product called Marketplace. Marketplace is it's all written using Scala. Massive amount of Scala. Huge amount of Scala. The project's been going since I think 2010. I think is like when the first kind of lines of Scala were written. So it's quite old Scala code, but it's actually the best Scala code I've worked on by far. Atlassian Marketplace. It's like an app store for our Atlassian products. So if you want to install a plugin for Confluence to, I don't know, email, it looks like, or get Gantt charts for Jira issues, you can come in here, and then there's a little button you can press to install it into your Jira. So it's basically just a big, a big web app to to sell plugins. We make a lot of money off it. You can look up Atlassian Marketplace and you'll find some like press releases about how much money we make. It's a really profitable thing for Atlassian, and it's all done in functional programming. It's a massive success story for functional programming at Atlassian. Okay, and so that's all deployed. So it's written in Scala and it's all deployed using. It's like 90-something% Scala probably. There are some services that are written in Haskell, but they're not completely critical. They're good to have, but they're not critical. And it's all deployed using a tool called Nix, which is a functional kind of package manager. So we deploy using Nix, and it's all written in Scala. It's a good project to work on. I really like it. Okay, so yes. So list of list. If you give me a list of lists and you give me nil, so you give me an empty list of lists. Flatten nil is nil, right? Flatten nil should be nil. So that should be probably the nil. Replace nil with nil. I think that makes sense. But here what we have is cons needs to take a list of A's and a list of A's and gives back a list of A's. And what did we just write? List of A's, list of A's, list of A's. So we've got something that matches that. So if we just replace cons with something that type checks, let's give that a go. Flatten that. So what this is going to do is replace our cons, right? Replace our cons with plus plus. Every time you see plus plus, replace it with, every time you see, every time you see our cons in our outer list, so not in our inner list, but every time you see cons in our outer list, replace it with plus plus. And that does do a flatten. And so really our flatten should work because that's exactly what flatten is doing. It's just going through and every time it sees cons, replace it with this plus plus. And that's all that flatten is. Just go through, replace cons with plus plus. So it just pluses these together. Concatenates them all together. Easy. Alright, so Flatmap. So we're going to take a list and we're going to produce a new list. Flatmap on a nil should be nil. Straightforward. So we should only really have one thing that we need to fill in cons. This is just common pattern. Just try fold right. If you're taking a list and you're producing a new list, nil goes to nil. What can you do with cons? That's just a, it's just a kind of a feeling that you get for it. Like there is more implementations than this. There is kind of more things you can do, but by default, you can kind of look at this and say, well, I'm probably gonna go through every element. I'm gonna replace cons with something, and well, nil with nil because I'm taking a list and producing a list. So flatten, plus plus, etc. are standard container APIs or like operating overloading. Not really either. These are just functions we've written. We've written a function that takes a list of lists and gives back a list. There's no standard API for this. You just call flatten. It works on lists of lists. It's just because we got this module, it's course.list, this module. So because we got this course.list module imported, we can use flatten. There's no operator overloading. There's kind of no abstraction behind this. It's just we are writing a function that works just over list. There's no standard API. There's no kind of consistent way. So I can't say flatten. I can't run flatten on something that we had just before. So we had a full one. I can't run flatten on that. So we're not kind of using any like API or interface to do this. We are only just running it on list at the moment. We will eventually get to like being able to write flatten. It won't be called flatten, but we will be able to write flatten on more than just list eventually. We will get there, but it's not yet. And it won't be called flatten either. Flatten, we've written flatten and it just works on lists. We'll write something else that does something that provides a general interface to flattening things. Okay, so cons takes an A and a list of B and gives back a list of B. But what do we have in scope? How can we get a list of B's? Well, we've got this function f which takes an A and a list of B. How can we get an A? Well, we've got this cons function, right? So let's bring that in scope. Let's bring A into scope. A, B's. Okay, so to do needs to give back a list of B's. What we have in scope is we've got an A, we've got a function that takes an A to list of B. So to do could be F running with A, but then we've also got this B's in scope. What can we do with that? Well, we don't just want to drop it. Yeah, we could do that. So we could say flatmap equals flatten of map f of x's, right? So that type checks, map through each one, then flatten it. That makes sense, we could do that. That's probably actually a better solution in the end in a way. Actually, let's just go with that, right? Let's just go with that. So, let's go for that. So we've got, let's try and derive that real quick. So we've got x's in scope, and we've got, so we need to give back a list of B. What do we have in scope? Well, we've got a function that goes A to list of B. So if we map x's, we'd get back a list of B's, right? So let's go with that. I haven't showed this syntax before, but basically let in. So when we say let, we're creating a new identifier. So we're saying B's is equal to that in this, and this is the scope we have access to. So if we reload this, you should see that we've got B's now. We've got a B's. So it's just variable binding. It's just like it's just assignment, just assigning a new identifier to a value. So we've got B's. Now we've got list of B's. So what we've done is just run this function over every element in our x's. So map, remember map that takes every element in a list and runs a function over it. So we've got a function that results in list of B's. So now we've got a list of B's. And what Worldender pointed out is that we could just run flatten on our B's. Remember flatten, whoops, we don't have it in scope because it didn't compile, but if we run, type of flatten is take a list of A's and give back a list of A's. And remember that what our whole was list of B's, so we had a list of B's, so take a list of B's, flatten it, so that means we just get a list of B's. That type checks and fills in our hole that we have. So we could just do that. Map. Let's get rid of this binding. We don't actually need this intermediate binding, so that's the same. And so there's another trick we can do if we because we've got this x's on the left hand side and we've got something on almost on the right hand side. So notice how this is almost on the right hand side. What we can actually do is do something called composition, which converts it into that. So that's exactly equivalent to what we had before. So composition is basically just combining two functions together into one big function. Definition of composition is f.g is f.g is the same as, that's the same. So composition is just if you have a function. So we can also lift this out. Remember that we've got lambdas, so x. So that's the same. So when you compose a function together, what you're doing is really just creating a new function that just runs both of those functions on a value. So if we did that transformation here, then we've got it into a form that the left-hand side of the equal sign the last thing on the left-hand side of the equal sign is the same as the last thing on the right-hand side of the equal sign. So we can just drop that from both, and we end up with that. And then you can do that same transformation like I did before, so I could go compose, I can't even remember it. Is it compose that with map, and then we can drop F. So you can go even further, but it starts getting really, pretty ugly. So it takes like takes a couple seconds for me to come up with that, so I usually stop about there. I think that makes sense. And so even though this would be like this, you starting off with Haskell, this would be harder for you to read than, you know, actually than writing it like that. Sorry. Like, if you're starting off with Haskell, this will be more readable to you, but eventually this form becomes more readable. Eventually, enough practice, this does become more readable. So I do recommend, if you're doing the FP course, try and aim for writing things like this, because eventually you've got enough practice that this becomes more readable. It becomes quicker to read than the alternative. You do eventually get there. It does take a while, so I recommend a lot of practice. And so if you're doing the FP course, try and practice that. There's tools that you can install. You can install something called point free. So if you've written a function, you can use point free, and Haskell will print out, like the point free program will print out, you know, what you could write instead of that. And then if you're struggling to read someone else's code, you can use something called point full. So const, for example, and it'll flip it over. Or you can use my bot. I've got a bot. You can type in PL, and then if you type that into chat, it'll print out const. Or you can write point full const, and it'll do the other way. It'll flip it around and print out that. So you can use my bot, or you can install those programs. They're very useful to have. Cool. So that's a good implementation. Thank you, World Ender. That's a good one. You call it pointless, not point free? Yeah. That's the pun. That's the implication. Yeah. So we're gonna write flatten, but this time, right? So last time we wrote flatten, we used fold right, concat, and nil. But let's write flatten, but let's use this flatmap function. Const is constant in Haskell, but in a different way. So const is the constant function. So the constant function means give back the first argument and ignore the second argument. My solar power consumption, still running that program to track it. So update on my solar thing. I am running that program. It crashes every night for some reason. It used to not crash, and now it does crash, and I don't really know why. Every night, probably somewhere around midnight, I get like that weird error from the service that I use. I forgot what the service is called. What is that service called? Yeah, I've forgotten what it's called. So it runs, but sometimes it crashes, and so I haven't set up any daemon or anything to restart it. If I go to my Twitch page, actually, I'll find a link to it. Oh, it's PV output. That's right, PV output. Here we go. There we go. So this is, you know, I usually run it, but yeah, see, look, it crashed at midnight. So I don't know. Sometime when it sends it at midnight to PV output just says error, and then it crashes. So yeah, I don't know. That's annoying. Oh, actually, that was about lunchtime, right? PM. So at AM, yeah, that was about lunchtime. It crashed. I don't know. And this was actually a couple days ago. I've had to restart my computer. I haven't started up the script again. So what I need to do is make it resilient against PV output being weird about sending things around lunchtime. It seems to be like a common, like a standard time. Like if you send it, maybe, I don't know why either, because like it was working for weeks on end where I didn't have to restart it, and then all of a sudden it stopped working. So I don't really know what happened there. So I need to fix it up, make it so that it actually just, you know, retries or does something about missing data, so it just doesn't crash, so I don't have to keep restarting it. It did work for weeks on end without me restarting it. So that's one update. So I do still try and submit the data, but I haven't submitted it since a couple days ago. But I do try and still update, you know, send the data. I ran into a problem with my batteries and everything, in that I tried to make a cable that would plug into my Dell computer, and it worked. I had a cable and it would plug it in, and it would actually send power to my Dell computer. But Dell has something called a Dell One Wire. They've got this thing called Dell One Wire. So actually, their chargers actually talk a little protocol. So you plug in your charger into the Dell computer. It actually talks a little protocol, and the protocol is how much the charger is able to deliver to the computer. So my computer demands like 130 watts, and so the little charger needs to send a little protocol and say, hey, I'm going to be able to send 130 watts. Otherwise, if it doesn't send anything if it just provides power, Dell assumes that the charger isn't capable of delivering 130 watts, and so underclocks itself. So my computer underclocks to like 1 gigahertz down from like 3.3 gigahertz or whatever. So it underclocks to 1 gigahertz when I plug in my charger. So it actually makes it awful. Hey Aman, how's it going? We're trying to go through well, at the moment I'm talking about my solar thing and all the problems I've been having. But I'm trying to we're going through this functional programming course. I'll finish up my So basically, Dell underclocks its computer if I try and make a non-genuine charger. If I make my own charger, Dell underclocks. It sucks. So what I'm doing is I'm just giving up basically on making my own charger. I'm just buying a little inverter. I'm just going to plug it in, and it would cost me $50, but to me it feels like I'm admitting defeat. I'm being defeated by my own laptop, and it sucks. But it'll work. The reason why I was trying to make my own charger and everything was to be ultimately like the most efficient. I wanted to have everything in my office be as efficient as possible, but that's not going to be possible. I'm just going to chuck a noisy inverter below my desk, and I'll live with it. Kind of sucks that Dell has its own protocol. Well, it's not even its own protocol. It's actually used by Apple as well. They have like some weird proprietary protocol for you to talk to be able to tell. To tell the computer that it can get charged. It sucks. Anyway, I'll live with it. Anyway, so we're going through Dell FP course. It is the Data61 FP course. It used to be called the NICTA FP course. It's maintained by these people, Queensland Functional Programming Lab. They go around Australia teaching people Haskell, and so they use this course. It's really good. I use this course at work. A lot of people. There's probably like 20, 30 people at work that have gone through the FP course. And it's pretty popular inside of Atlassian. There's a little chat room that people use to talk about on that. It's a very good course. I really like it. So I went through like just the syntax of Haskell. I went through a couple of libraries. There's a validation, which is just a data type that represents error types and successful values. We went through exactly1, which is just a really simple data type just to show just how you write data types in Haskell. We went through optional. We went through all the exercises in optional. So optional is a data type that represents, either you've got a value or you've got no value. Went through that. Now we're going through list, and we're focusing on fold rights. Yeah, the NICTA are the people who did the L4 kernel, and exactly, they did SEL4. NICTA is no more. Australian government came in, different, politics came in basically, and they cut funding for NICTA. So NICTA basically disappeared, and now it's turned into something called Data61. And they merged with something called the CSIRO, which is the Commonwealth Research Organization down here. So, politics got involved basically. So NICTA's no more, but the projects are still going on. They basically just turned into a different company called Data61, which is partially owned by CSIRO or collaborates with CSIRO or something. I don't know. But yeah, SEL4, really cool kernel. They actually, if you are interested in, oh, thank you so much for that, Aman. Thank you so much. Thank you for that. So SEL4 is a project for it's a verified operating system. Problem with learning Haskell is you get used to some awesome features it has, then you'll be miserable at work. I just get my work to use Haskell because it's the most practical tool out there. That's the way to do it. So SEL4 is like a verified. So if you want to come to Australia, you can talk to these people because they are always hiring. Like if you're interested in logic or proofs or anything, these people are always hiring things that like proof engineers. So proof engineer Data61. So if you're interested in proving things, or you want a job doing like Agda or doing this is not actually Agda. It's something called Isabel that they use a lot of. But if you're interested in what I was doing last week with writing Agda. Talk to these people. They're awesome. They do, they actually provide jobs for people that do proofs. So if you want to do proofs as a job, talk to these people. Okay. No one at your work will believe that Haskell is the most practical tool. You just have to show them. I mean, that's what I'm doing. I've got a really good course for you to to use to show people that Haskell is the most practical tool. Hopefully, I mean, hopefully, if you watch this, you'll gain some experience. You'll gain some knowledge about how I teach Haskell anyway. You might be able to use some of the tools that I use, some of the explanations I use. Had the Stack Exchange question unanswered. If anyone in chat wants to take a view, I'll have a look after I do the stream for sure. Learning some Dean, I just stopped. It's too cool, but I can't use it at work. Alright, so we're going to go flatten again, but we're going to use Flatmap. I'm going to get through a couple of these real quick, and then I'll stop the stream. So let's use Flatmap. Oh, look. They've even given away the answer in this. That's not good. They've given away the answer right here. I might have to submit an issue about that. They've just given away the answer. So implement Flatmap using, flatten using Flatmap. So let's try and use Flatmap on our, I'm going to assume, what can we use Flatmap on? Well, there's only one list to really use it on. So Flatmap F on our list. Come over here, what do we see? We need to implement this function, list of A to list of A. What can we do with, how can we make a function from list of A to list of A? What can we do with that? Well, identity function. So there's a function called ID, which, you know, just takes takes any value and gives back a value. So ID1 is a 1, ID2 or ID3 is 3, ID true is true. So it just gives back the argument. So what if we did a flat map with ID? That type checks, right? So let's go flat map again. Oh, flatten again. Sorry, flatten again. So we do flatten again. What did we have before? What was our flatten argument? This thing. This big thing here. Same thing. So flatten and flatten again are equal. Different implementations, but they're the same function. So we can just use so what we've done here is what we've shown is that we can use flatmap to implement, sorry, we can use flatten to implement flatmap, and we can also use flatmap to implement flatten. So, you know, depending on which one you implement first, you could use the other to implement the other one. So that's really interesting. There's actually some maths behind that. We'll get into that later on, but you can either implement flatmap or you can implement flatten. Up to you. That'll be interesting later on when we get to something called a monad. You can implement flatten or you can implement flatmap. And the monad has something. What we were getting at before is, like, you know, the general interface. What's the general interface? That's interesting. When monad is called is the general interface for this flatten idea. And so the idea is that you can implement either flatmap or you can implement flatten. That's interesting to think about later on. Yeah, okay, so let's implement one or two more and then talk about some things. Said the M word. Okay, so seek optional. So remember our optional type, right? Remember our optional. Optional has full or empty. So I'm just going to default right, because that's a good default. Right, but I have to give back an optional. So that's interesting, right? So what do I do? What would I replace if I have if I've got a list and I need to replace nil with something to make an optional? What could I do? Here's the answer. We've got a test that says exactly what it is. So seek optional on nil is full of nil. So looking at the test, there's actually a couple of things. So we could have actually said, you know, it's empty. Could have said it's empty, and that will type check. But our test actually says up here that that's not the implementation. It's actually full of nil. Flatmap F is flatmap id.mapf. I'm confused by that because that's like recursive. It looks like infinite recursion to me. Is there world ender? Is there did you make a typo in that? Oh right, yeah, I see what you're saying. I see what you're saying. Right, yeah. So right, you need like a base case, right? You need to you can. I see what you're trying to say. Yeah. So flatten. If you could use flatten again. So what if we did this? Flatten again. flatten again mapf, right? Because then what we're saying is flatmap ID is flatten again dot mapf. So it's like it's an infinite recursion, yeah. That, you know, obviously that would be infinite recursion, so it would break. So we can't do that. Basically, what I'm trying to say, what this is trying to say is that it doesn't matter if you implement flatten or it doesn't matter if you implement flat map. As long as you implement one, you can derive the other. That's kind of the point. So you can derive the other by implementing one, but you still have to implement one. You can't just say, well, you know, flat map is the same as flatten, and flatten is flat map, so it doesn't matter. You have to implement at least one of those. So if you don't implement at least one of those, yeah, you'll have infinite recursion if you try to derive them. Does that make a little bit of sense, Word Under? Like, you have to implement at least one, and you can derive the other. So you really have to implement one. Okay, okay, right, so where we are is... we have this now. We have this whole, cons. So in implementing seek optional, I've put in a hole to replace what cons with, like what should we replace cons with. We know that we replace nil with full nil, because that's what a test says up here. The test says right here, seek optional on nil is full nil. So we've already got the answer for what to replace nil with. Replace nil with nil, but in full. And that's interesting, because what we're doing is replacing nil with nil, but it's in full. That's something to remember in a minute. So what we're going to do is use cons, right? Cons, we need to replace cons with an optional A to an optional list of A to an optional list of A. If you get rid of the optional part, it looks exactly like cons. You didn't know much about whole programming until today? Yeah, whole driven development is awesome. Really, you really should use this. Yeah, put underscores in and then just let the types direct you. So the types here are telling me I need to implement a function that's optional A, you know, optional list of A to optional list of A. And what's interesting is that if you got rid of the optional part, this is cons. So A, list of A, list of A. So that's the same type signature as cons, right? So that's something to recognize. Just look at that and you'll see cons. But it's working inside of optional. So we're kind of like, it's our cons, but it's inside of optional. So we're kind of lifting our optional into, lifting our cons into optional. And if we look at if we browse our optional, course.optional, if we browse this and we look through, there's this function here, twice optional. I'm going to give away the answer, but usually I get people to look through here and try and find out things, but twice optional is the one that you want to look at and see how it lifts a function into working over optional. So this is, you know, optional A, optional B, optional C, A, B, C. So if we give this cons, if we say what's the type of twice optional cons. Whoops. Oh, right, because it's not compiling. Twice optional cons gives us back cons, but working inside of optional. So that is what we want. We want. I mean, that makes the types line up. So if we do that, the types line up, and what we like, I'm gonna give away. I'm basically just gonna go through this really quick and give away the answer. So full nil. So nil we've lifted into using optional, so we just used full to lift nil into optional. And what we've done is lifted cons to work inside of optional by using this twice optional function. So what we are doing, what you can think about seek optional as doing, is so it takes a list of optionals, but then kind of like we've got a list of optional things, and it deconstructs the list, and then reconstructs it inside of optional. So that's the interesting thing. You're deconstructing the outer thing, deconstructing list. So seek optional, we're deconstructing the list. Now we've got an optional, and we're reconstructing that list, but inside of the optional. So we're kind of flipping it. So we're deconstructing the outside thing and then reconstructing it inside of something. So that's where you can think of seek optional. There's actually a generalization of this called sequence. And that's the general thing you're doing. You're deconstructing the outside thing and reconstructing it within within the what was formerly the inner thing. You're reconstructing it within that now, so it becomes the outer thing. So you're kind of flipping the two type constructors, but deconstructing the outside thing, reconstructing it within another thing. Hopefully that makes sense. And you can see this here. You can see the pattern right here, because fold right is deconstruction, and what we're using is cons and nil. And remember, fold right, take the first argument is cons, second argument is nil, what you're going to replace it with. So what we're replacing cons with is cons that works inside of optional. Twice optional is a function that takes a function and puts it within optional. So we can say twice optional plus, and so I can say full 1, full 2. And what it does is just run the function, but inside of optional. So it kind of lifts this function to working over optionals. So hopefully that makes some sense. From the above, we can derive flatmap f nil is flatmap id nil, assuming that map f nil equals nil. Not hopeful, but maybe for a correctness proof. Maybe flatmap. Yeah, I think okay. Yeah, that's true. That is true. Yeah, maybe for a correctness proof. Yeah, that could be useful. Okay, so there we go. Hopefully that implementation makes a little bit of sense. What we're doing is lifting in, we're deconstructing, then replacing the constructors with the constructors, but they work within optional. That's the thing to think about that. Okay, so I've been going for 3 hours. I'm going to finish up about there. Does anyone do we want to keep going with going through the FP course? Does anyone like this? Would anyone prefer not doing the FP course, or? Can you save today's VODs? Yeah, absolutely. I think this one would be useful to a lot of people. So please let me know if you'd like to see me do more of FP course. I can pick up where I was, I can pick up and do fine next time. Next week I can do fine and we can pick up there, or let me know if you'd prefer something to do more like project-based stuff instead of me going through and teaching Haskell. Would you prefer me to go through and work on a different project? What do you want to see? Do you want me to keep going through with this FP course, or would you prefer me to work on something else? Let me know, and I'll look through Twitch and find someone to host. Definitely this? Awesome. Cool. Course is fine. Okay, sounds good. I'll keep doing with this then. We'll pick up, I'll pick up and keep going through lists then. There's actually some really good discussion we can have. This not reverse is a really good thing to discuss. If you wanna, I'm going to commit this, I'm going to put it onto my fork, I'll post it below, I'll put it onto my Twitch page. If there's something you wanna, if you wanna practice some things, have a go at all the, have a go at the exercises, but in particular, if you wanna have a discussion next time, have a look at this not reverse. Have a look at not reverse, it's a really good discussion point. Try and find another implementation for this function. Thanks for the follow. And thanks for all the questions you've been asking lots of really good questions. That's awesome. Thank you. So next time, if you wanna have a good discussion, look at this function. It's a really good exercise. Is there anything other than reversing a list? Is it possible to implement this function? And look at these tests and try and think about what you could do to implement this function.